Okay, I'd stopped the stream for a while. Hey guys, so I switched off the audio input capture. I'm really sorry. Okay, so let me start over again. Just it'll take 2 minutes. So I'm Advait. So in this stream, we'll be continuing our discussion on return-oriented programming. So in the previous stream, we discussed the first three sections of the paper, which were introduction, background, and the X86 architecture. We went to fairly good detail, I would say. We had a couple of demos. I hope you guys understood what was happening under the hood. So in this stream, we will talk in detail about return-oriented programming, section 4 and section 5, which will talk about gadgets. So we encountered a word called gadget. So we'll be seeing how gadgets, various type of gadgets can be made in section 5. So these two are the core, two important sections of return-oriented programming of this paper. So without further ado, let's get started. Let me see if someone's online. Okay, let me just put a message. Okay, so if you have any questions, feel free to put them in the comment section. So I'll be checking, polling for questions now and then, so don't worry about it. Oops. Okay, so let's get to the paper. So this was how we, okay, so now the setup is fine, and on the other side we have the scratch pad. So this is where we stopped. So I'd given you two simple exercises using mprotect to change the stack permissions and then try traditional code injection, and to implement a more complex return to libc attack. So there was a reference in the paper to an attack where multiple libc functions were chained and then called. So instead of just calling system or execve or exit, multiple functions were chained and then they were called. So that was one more exercise. So today we will start here. Okay, return-oriented programming. Principles of return-oriented programming. In this section, we lay out the principles of return-oriented programming, comparing it to the traditional way in which computers are programmed for legitimate purposes. While our examples draw on X86 assembly, the principles are widely applicable. The principles we describe are the result of working out the implications of the following. How should programs be constructed if the stack pointer takes the place of instruction pointer? So this question is the foundation of return-oriented programming. So we'll go through it again. Let's read it again. Let's try to understand. How should programs be constructed if the stack pointer takes the place of instruction pointer? Okay, so that's the foundation. So in normal programs, instruction pointer, the RIP or the EIP register in X86 always points to the next instruction. Basically, it has the address of the next instruction which will get executed, right? Oh, unless there is a jump or a control flow diversion, so jump or call or something like that, the instruction pointer will always point to the next instruction. So that is how normal programs work. But here the question is, how should the programs be constructed? How will the program look like if the stack pointer takes the place of instruction pointer? That is, how will the program look like if the stack pointer always points to the next instruction? So let's write it down. Let's write what we understand. How will the program look like if stack pointer points to the next instruction to be executed? So this is one. This is another way to put the foundational question. So let's read on. Okay, program layout. An ordinary program is made up of a series of machine instructions laid out in the program's text segment. Each instruction is a byte pattern that, interpreted by the processor, induces some change in the program state. Okay, so the program structure of a normal legitimate program is very simple. So let's open up one more window. We had actually written a program in the last stream. It's a very simple program. You can actually copy it down. So it has a main function which calls a function func, and then the func allocates a buffer of 100 bytes. It requests for user input using the getS function, and then it prints it back. It's basically an echo program. So these two functions are the ones which we wrote later for some other purpose, so don't worry about it. So we'll be using only main and the func. Okay, so you can copy them down if you want. So okay, so let's compile it. Oops. Okay, so the compiler flags, let me explain it in short. So the -M32 stands for machine 32. Basically, I am running a 64-bit system, but the paper revolves around the 32-bit X86 architecture. So I need to request the compiler to generate a 32-bit executable. So that's why this M32, it signifies that. The fno stack protector is, so for the demo to work, for the exploits to work properly, we need to remove security protection. That's what we are doing. It's telling F stands for flag. It says no stack protector, and G is, it'll add some debug symbols. It'll be easy to debug, right? So it gives some error, warning. So that's all okay. We will try to run them. So this is what the program does, right? So here, so we were actually originally talking about the program layout of an ordinary program. So this is an ordinary program. An ordinary program is made up of a series of machine instructions laid out in the program's text segment. So when we run it, so we can actually look at its text segment, for example. So we can go to its maps file, and so this is how the complete memory layout looks like. So it has the text segment. You can see that it's read, no write, and then execute. So it's fair to say it's the text segment, and then there is the read only part, which has all the string literals, which is read only, they cannot be changed. And then there's read write, which is the data section here, and then rest of it. There's heap, there's libc mapped to the process's virtual address space, and then later there are other address ranges too, including the dynamic linker and the stack. So this is what we are talking about. This is the text segment. How is this? How does it look like? So here we see that it starts from 5000 and goes till 6000. That's one page, 4096 bytes. So how does it look like? That's what we want. So we can actually go, we can check this off. We can look at its disassembly code1.obj, right? So it says init plt. There are other sections too. Oh, this is where our text starts, right? So it starts here. So you can see it's a series of instructions. It's an array. It's a, you can think of it as an array of instructions, and goes on main. So we saw simple func. There's func up there. There's main. There are other functions too, and then it ends here. It ends here, and then some other sections start, right? So the program structure of an ordinary program is fairly simple. It's just an array of instructions, and each instruction is a byte pattern. We have seen that in the previous stream. So what type of byte patterns and all that. So the instruction pointer governs what instruction is to be fetched next. So this is what we were talking about. To understand this, we can just break here, break at main, and then run. So we can look at the EIP, the instruction pointer. It has some address 565555F4, and then it points to the next instruction to be executed, subtract ESP, 0xC. So note that these addresses can change from it can be different from my system to your system. Your system can show some other different address, but the idea is all the same. So EIP, it points to the next instruction to be executed. This just got executed, this will get executed. That is the idea. Next, it is automatically advanced by the processor after each instruction, so that instructions are interpreted in a sequence barring a jump or other transfer of control flow. So it's very simple. It is automatically advanced by the processor after next instruction. If we go to next instruction, see, it's automatically advanced. It was pointing here, and now it's pointing to the next instruction. It was advanced by the processor, right? So that the instructions are interpreted in a sequence, in a contiguous manner, one after the other, barring a jump or other control flow. Yeah, so here, so we move two instructions and then we have a call here. So that's a transfer of control flow. We are transferring the control to put s. So here that sequence doesn't work. So the sequence is diverted, control is transferred to put s, and then it comes back. So we can step into it. See, now we are now we are in put s. So we continue, put s is big, okay, oops, I'll break here and just let me just continue. So that call ended and we are back, and now it's pointing to the next instruction. So that's what they mean. A return oriented program is made up of a particular layout of the stack segment. Each return oriented instruction is a word on the stack pointing to an instruction sequence in the sense of ordinary programs above, somewhere in the exploited program's memory. So what does that mean? So a return oriented program is made up of a particular layout of the stack segment. The stack segment, you can think the stack looks something like this. So today we will be using Google Drawings. So I thought it's better than the the app which I was using before. It's very simple. It has limited tools, but it's good, I can say. So the stack looks something like this. So let's it has a width of 4 bytes. I want a double-ended arrow. Okay, never mind. It's okay. We'll just use the line. So this is 4 bytes. So this is 4 bytes, and then generally the ESP always points to the top. Right? ESP points to the top. So what they're telling is the return-oriented program is made up of a particular layout of the stack segment. So okay, let's see how that layout is. Okay, let me repeat it again. In an ordinary program, the layout is fairly simple. All the instructions are set in a sequential manner, in a contiguous manner, one instruction after the other, and the RIP keeps, and the instruction pointer keeps moving to the next instruction unless there is a jump or a transfer of control flow. Okay. Each return oriented instruction is a word on the stack pointing to an instruction sequence. So here we come across a very important word which points to an instruction sequence. So we already saw in the previous stream that an instruction sequence here, like they are referring to any instruction sequence which ends with a RET instruction, right? So there are a lot of RET ending sequences. We can actually, I think there's one right. See, this is one such instruction. So let's just copy it down to understand better. Oops. Okay, this is bad. Shit. Okay, I could have just done this. So it's pop EBX and next RE followed by RET. So this is an instruction sequence. So how can we put the address of this onto the stack? That is the question. So it's a word on the stack pointing to an instruction sequence. We can know the address of this instruction. How can we do that exactly? We can use GDB for that. So we know that the offset is 3B9 here, right? So just use code one and then main run. So assuming it starts from here, I mean the offset is here, x to I. Let us try to dump 2 instructions, and then what was the offset? 3B9. So here we go. So this is the actual instruction, right? 56555 3B9 is the address of this. So in the last stream we saw how to overwrite the return address on the stack. So we'll do the same now, and we'll make sure the overwritten return address points to this instruction sequence, right? So we'll come out of this. Let's go back to our beloved exploit.py, which we wrote. You can just copy it down. One thing is, it's better, it's always good if you watch the previous stream and then watch this, because we covered a lot of prerequisites. We also saw a couple of exploit demos, so I won't be repeating them again. So I request you to watch it and then continue, right? So okay, so return stack address, buffer address, these may actually change. That's okay, we'll update them. We'll just remove all this, it's not needed. So there is a gap between the buffer starting and the return address. We fill in the gap with crap like A, basically a series of A, and then we need to jump here. So this actually points to pop EBX, RET. So this is what is happening. So we can stop this, and then we can run this. So now payload.txt has the input, has the crafted input. So let's go to GDB again. Let's break at func. So we are at func now. We'll go instruction by instruction. oops, okay, so I had to do a run payload.txt. Here we go. So now we are in func, you can see that. Let's go. Now the input is taken, it prints the input. Okay. Now look at it. So we are about to return, but the return address has been overwritten by our new address. See, the return address is always at the top when RET is about to get executed, right? So it points to this. So now if I go to the next instruction, where will the control flow go to? Will it go to main, or will the control be transferred to this instruction? It will obviously be transferred to this instruction because there is the return address is now this. So we'll just do ni. So here we are. So now we are about to execute pop EBX. Don't worry what this sequence can do. Pop EBX will pop this value, some value into EBX. That's okay. Don't worry about the meaning. But what you need to understand is there was an address in the stack, as they told in the paper, and that was pointing to this instruction sequence, right? So let's go back to the paper once again and the scratchpad. So we made a stack. So we did something like this. Where is the text? It's here. Yeah. So we put the address, which is some number. What was that? Okay, it was this. Which in fact pointed to this. Right? So this is how that setup was. It was very simple. We overrode the return address of main of the func with this new sum address, which we knew points to pop EBX and RET. So what they're telling in the paper is a return oriented program is made up of a particular layout of the stack segment. Each return oriented instruction is a word on the stack. See, this is the word is 4 bytes. This is the word on the stack, pointing to an instruction sequence. See, pointing to an instruction sequence somewhere in the exploited program's memory. So this is a very important point. So we didn't inject anything. We didn't do anything of that sort. This instruction was originally there in the memory, right? In the program's memory at this address, it was present. So we simply put the address here and then it is pointing to this now. Correct? So this is a very crucial statement. I hope you understand this. So if there are any questions, just please put it in the comments section. So don't worry about it. So we have a question from C. Keshava. I think that's my friend. Okay. Can't we use step or next to come out of put function? Yes, we can use it. But the problem would be that we have not set the, breakpoint after the put test. What I mean is, okay, we'll just run it again. So say we are here. So what you're trying to tell is we can we go into this using step, and then you're telling if we can't use step or next. We can use, so we use the next instruction, we go instruction by instruction. So say we continue, right? We just keep doing ni. So yes, we will have control, but what I wanted to do is I didn't want to see what putters was doing. I just wanted to come out of it. So if we just try to come out of it we'll just go out of it completely. So what I instead wanted is, I wanted to come here. So I wanted to stop after putters. So I had not put a break point here. So if I did a continue, I would just go executing all the instructions after putters. I would not stop after putters. So that is why I had to put a break, and then I had to do that. So I hope you get my point. Okay, let me just repeat. So we entered the putters, and then we could have used we have two choices. We could have used the NI instruction, basically the next instruction, and then we could have executed one instruction after another. But I didn't want to. That was not the point. We didn't have to see what was happening inside putters, so we just left it. And if we had continued using the continue instruction, because there was no breakpoint at this instruction, we would have just run, and then would have gone out of func. But I actually wanted to stop at this point. That is why I set the breakpoint first and then continued. So that was the idea. Okay, so going back to the paper, somewhere in the exploited programs memory, right? Okay, so sorry, before the question, we were talking about this. Where was this? It's, sorry, I'll just hide this. Okay. We were here. So we put an address here. That address is definitely a part of the program's virtual address space. It's part of the program, and it's pointing to an instruction sequence. That is where we are. Okay. Let's continue. We can see, we can think of these pointers as being byte patterns in an idiosyncratic new instruction set. Okay, so in the previous stream, they were talking about a new instruction set for return-oriented programs. So you know what an instruction set is, right? So in the X86 architecture, the instruction, there are a lot of instructions. We saw move, we saw pop and push, we saw add, increment, decrement, etc. So they are all instructions. So they all combined together make an instruction set. So here, what they're trying to tell is this pointer can be seen as the byte pattern of a new instruction set. So so they are considering an ROP program made up of a new instruction set, where each instruction is basically the instruction sequence here, and this is the corresponding byte pattern. So that is what they are trying to tell. Okay. The stack pointer governs what return-oriented instruction sequence is to be fetched next in the following way. The execution, we'll just read through. The execution of a RET instruction has two effects. First, the word to which ESP points to is read and used as the new value for EIP. See, that's what we saw. So this is read, correct? This is the word, this is read, and then it is loaded into EIP. So we can go back to this, and then we can run it again to see what. So we'll just go to func, right? We are here. So this is the word. The ESP is pointing to that sequence. If we execute RET, the first effect is that is read, this word is read, and then loaded into EIP. So look at EIP, it's some other value. Now we will do an NI and look at the EIP now. So that is the address which was there on top of the stack. So that is the first effect. So let me read it again. The execution of a RET instruction has two effects. First, the word to which ESP points to is read and used as a new value for EIP. Yeah, we saw that. Second, ESP is incremented by 4 bytes to point to the next word on the stack. So this we know. So what does RET do? RET is a complex instruction. It can be broken into two instructions. So two smaller, more primitive instructions. So these are the two. One is reading it and loading it into EIP. Second is ESP is incremented. So ESP has moved. by 4 bytes, and it points to something else now, right? So that if the instruction sequence now being executed by the processor also ends in a RET, this process will be repeated again, advancing EAP and inducing execution of another instruction sequence. So this is where this line is actually the crux of return oriented programming. So what we saw now is we just transferred the control to one instruction sequence. Now we will see how this sequence can transfer control to another instruction sequence. Yeah, we will go back, we'll find another sequence first. We'll go back to the disassembly. Okay, so we'll search for RET. Okay, there are a lot of RET instructions here. So we'll simply take this. Okay, so it's at an offset of 450. So let's make a note of that. So after this, we have a move. What was that? Move EBX dword pointer ESP. Right. Move EBX comma dword ESP RET. Right. It's at an offset of 0x450, which means its address would be at. We can find that out. Going back here, taking this, so this is the virtual address space, so 450, right? So here we go. So this is the virtual address of the next instruction sequence, of the second instruction sequence. So what we want to do is this simple. We want to do this. First, we want to execute pop EBX RET, and then later we want to execute move EBX dword ESP RET. How can that be done? So think about it, right? So we know how to execute pop EBX RET. We just need to overwrite the original return address with the address of this, with the address of pop EBX RET. But then how can the control be transferred from that to this? So we'll look into that, right? We'll go back to our exploit. So this pop EBX RET, that is okay. Later, so here, where will it return to? There is an RET instruction at the end of pop EBX RET. Where do we want it to return to? It is simple. We want it to return to the next instruction sequence, which is this. So what is its address? Its address is 0x555 Just think where you want to return to. So it's move EBX comma dword ESP and RET. So let me reiterate it again. So there is the original return address. We use the stack overflow vulnerability and then override the original return address with pop EBX RET's return address, right? And then this gets executed. And when RET needs to be executed, where do we want it to return to? We want it to return to our next instruction sequence. So which is located at this place. So let us go back to our drawing and update it, right? Okay, this size actually might cause some problem. Let me just reduce the size. Now we have address, which is this, and this is pointing to move EBX comma dword ESP comma RET, right? So this is how the stack would look like, right? So we'll go back and run the exploit. Now payload.txt has the stuff. So let's go back to GDB, right? We'll break at func as usual and run it with payload.txt as input. Okay. Okay. The input is taken. It's there, right? So we are here. We are just about to return from func, and we know that it returns to this, right? So we will use the ni next instruction. Will return. So now, see, look at something interesting. So we are here at pop ebx. We'll execute it. Okay. Okay, I think pop ebx is a wrong choice of instruction sequence. It has a side effect, so I didn't think about it when we were discussing. So, okay, so what does pop do? It pops a value from the stack. So let's go back to expert. Okay, it's a good thing. So I can get to explain what's happening. Okay, this comment is not right. I'll remove this. So we are here, pop ebx ret. Pop ebx gets executed, right? When this is about to get executed, this is actually on top of the stack. And when we do pop ebx, this address is actually popped out of stack. So our exploit is actually failing here. It won't work, because ideally this should be on the stack and it should get popped only when this ret gets executed. But here, because of this pop, this is getting popped before. So okay, so what we can do is we will put a dummy value here. Zero x 1 2 3 4 5 6 7 8. So even if it pops, so some value should pop into ebx from the stack. So okay, dummy value to pop into ebx. So after this pops, this will be on top of the stack. So we'll go back. Okay, that's a good thing, but I didn't observe it. Okay, let's break at func as usual. Let's run. Okay, Geddes is done. So we are here. So now let us execute the stack before we do anything. So we are about to execute the first ever return instruction, the return instruction of func, and the stack looks something like this. So does it look like what we think? Okay, so top of the stack has okay, where is this? Okay, this is great. Top of the stack looks like this. So top of the stack has it has a word, the address, which is pointing to pop ebx ret, and then later it has, so this we saw that it doesn't work. So we have a dummy for ebx. We need it to be placed here. Okay, now here we have the address. Shit, this is actually worse. I need to keep doing this the whole time. There should be a way to set this. Okay, so here we put some address. I think it was 0x565555450, which points to this. Okay, so this is how the stack looks like. We will go ahead and execute the ni. So the top is popped now. ESP is no more pointing to this. ESP instead is pointing to this. See, I hope you get the point. So ESP is not pointing here, it's pointing here, and this is out, it is gone. So let's remove this. So now we are executing pop ebx. So let's execute, right? Now we have one more RET instruction. What will get executed now? So here the top of the, okay, now it's the pop EBX has already gotten executed. So now the ESP again is shifted. Now the ESP points to some other address, which points to this new instruction sequence. So let us verify. X/word this. So what does this word point to? I stands for instruction here, X/I. So it actually points to what we think. So 2i. Okay. So this is the first, this is the second. So we'll go ahead and execute the RET, right? And now we are here. We are about to execute move EBX dword pointer ESP. So it is how we thought it would be. So first this instruction sequence gets executed, and then because of this RET, the next instruction sequence gets executed. So that is the planned. Plan. So if the instruction sequence now being executed by the processor also ends in an RET, the process will be repeated again, advancing ESP and inducing execution of another instruction sequence. What happens? So see here, even here there is an RET. What happens if we place another address here? That will also get executed. I think we'll do that, right? We'll do that. We will go back to this and we'll find one more RET instruction. Okay. So this is one more sequence. So we'll take this. It's at 491. 491, right? So we will go back to our exploit.py and so I just copied it. 91. So what does this point to? It points to some leave RET. So it's actually pointing to some function's epilogue, basically the ending, the last few instructions, right? So this is the idea. So this gets executed, pop EBX RET, and then this gets executed. Because of this RET, we want the next instruction sequence to be this. We want this leave RET to be executed. So we will run this. Okay, and then go back to GDB. We'll break at func, and then we will go ahead and see what happens. Okay, so we are about to return the first return. We are at pop EBX RET, right? Now the dummy value is popped into EBX. That's okay. And then now here we are at the second RET. We need, according to our calculation, we want move EBX dword ESP to get executed. So we will go to that. So we are here, move EBX dword ESP, right? Now we are returning. Where does it return to? We want it to return to leave. So we'll take this address and check, double check what's that. Leave RET. So this is where we want it to go to. Okay, so it's segfaulting, I know. So leave was not a good choice, but the idea is that, so you can see as and when we stack addresses here, where did that go? So we put one more address here. We put one more address here. Some 0x56555491. So that was in fact pointing to something else. Okay. Shit, this is bad. Okay. Leave RET. So this process is never ending. We can keep doing that. So because there is an RET, we could put one more address here, which has an instruction sequence ending with RET. So if it's ending with RET, so say we have one more sequence. I don't know the address, so just INST1, INST2, but ending with RET. That's all I know. So this RET will execute and then point and then will transfer control to this instruction sequence. Then inst1 gets executed, inst2 gets executed, then RET. So we can actually transfer control to wherever we want, whichever instruction sequence we want, if the instruction sequence ends with an RET. So that is the point they are talking about. So this actually feels quite arbitrary. What we did was arbitrary because we didn't think what each instruction sequence would do. We just selected a few random instructions, say three instruction sequences, and then we chained them. Basically, we chained the instruction sequences by placing their addresses on the stack. So that is. So I hope now you're getting an idea of what chaining means, what a gadget means. So we were talking about it in the last stream, but we didn't go in depth. So this situation, okay, inducing execution of another instruction sequence. That is what we saw. Okay, this situation is illustrated in figure number 3. Okay, great. So this figure is really helpful. So this is the layout of an ordinary program. There are series of instructions, and IP keeps jumping from one instruction to the next. But here, this is how it looks like. See, stack pointer is pointing to some instruction here. Here they have considered the C library, but we have taken some other instruction sequence, I guess. That's okay. So there was an address here. There was in fact an address here. So that address pointed to pop EBX RET, right? Because it's a pop, we had to put some dummy value. That's okay. Later, the next it also pointed to some instruction sequence, but ending with RET. And then later the same thing, instruction sequence in one instruction and then RET. And this can keep continuing. So this is how the return oriented program looks like. It can be a series of words where each word can point to an instruction sequence ending with RET, or it can be immediate values like this. Immediate as in constants like this, right? So that is what figure 3 spoke about. Okay, so let's continue. Whereas for ordinary programs, the processor takes care of fetching the next instruction and advancing the instruction pointer. In return-oriented programming, it is the RET instruction at the end of each instruction sequence that induces the fetch and decode in a return-oriented program, like the carriage return key on a manual typewriter. So this is extremely, this tells what RET is actually doing, So in normal programs, how does the EIP change? How does the instruction pointer change to the next instruction? So that happens automatically. I mean, we as programmers or the assembly program doesn't have to do anything. The processor will do it. But here, the RET instruction is doing that. So if the ESP is pointing to this address, this instruction is fetched. Basically, this instruction sequence is fetched and then executed. So that is what RET is doing. So that is. Okay. The processor still takes care of advancing EIP within an instruction sequence, but this is now in effect an implementation detail. Okay, so what this line means is RET. Okay, so now we have two things here. One is ESP, one is EIP. What are these two exactly doing? Let us run it one more time and okay, sorry. We are in func, okay. So now we want this instruction sequence to get executed, pop EBX RET. So RET instruction, the RET instruction here is doing that job for us. It is fetching this sequence and then executing. So here inside the sequence, RIP is the instruction pointer is still incremented or changed by the processor. I do an NI, so this automatically points to RET. basically the next instruction. Here EIP is doing its work. Inside the sequence, EIP is doing its work. From sequence to sequence, RET. So let's write it down. To transfer control from sequence to sequence, RET comes to rescue. So it helps there to transfer control inside. So this is important. An instruction sequence. EIP only helps. The processor helps basically. Processor helps. So this is what is happening. So when you want to jump from one instruction sequence to another instruction sequence, RET will help. But inside one instruction sequence, if there are 5 instructions like this, for example, we have INST1, INST2, INST3, INST4 and then RET. To transfer control from some other instruction sequence to this sequence, RET will help. Once control is here, to transfer control from INST1 to INST2, INST2 to INST3, instruction 3 to instruction 4, EIP helps. Basically the processor helps in incrementing EIP. So this is what they mean. Okay. NOP instructions. The simplest instruction is the NOP, which has no effect except advancing the program counter. So it will except advancing the program counter. Instruction sets generally include such an instruction. On the X86, one can use the NOP instruction. In return-oriented programming, a NOP is simply a stack word containing the address of a RET instruction. These can be composed to form a NOP sled as illustrated in figure 4. Right, so NOP instructions has a really interesting use case when it comes to traditional code injection. So when we were talking about code injection in the previous stream, we encountered a problem. So the problem was, so we are here. We need to talk about NOP sled. So the problem was, what if the address keeps changing? So we had to jump to some place in the stack, basically the buffer. What if the buffer's address kept changing? So going back to our exploit, we can actually understand that here. So buffer address. Idea was store the machine code, the injected machine code here, and then overwrite return address with buffer address. That is, in theory, it works perfect. But what if this buffer address keeps changing? Right? So now we have hard coded it, we execute it, but then what if the address becomes some instead of what is it, FFFF C98C, instead of that it will become 0x FFFF1234, or it will change 98C to 99C or something like that. So NOP sled helps in making the exploit more robust that way. It can resist these changes in addresses. So to talk more about NOP sled, we'll come back to that later in the end, so that we'll finish ROP and then come back to talking about NOP instructions. So I don't want to disrupt the flow. So okay. Section 4.1.3, encoding immediate constants. Instructions in ordinary programming can encode immediate constants. For example, the instruction move 0x DEAD BEEF deadbeef, EAX, which sets EAX to the value deadbeef, is encoded as BB EF BE AD DE. Okay, we can actually see that. We can we can use RASM. It's radar's assembly and disassembly module. We can use that. What is that? Move. So we'll be using the Intel syntax. So move EAX, 0x DEAD BEEF. So this gave some machine code something like this. B8. So whatever is given here, I just wanted to show it to you, nothing else. So we are here. Move EAX, 0x DAD BEF encoded as this. Okay. So you can, I mean, it's very simple. The encoding is simple. We can understand that, but just by looking at it, B8, it actually informs that you need to move something into you need to move something into EAX, and what do you need to move? That constant is here. See, DE, AD, BE, EF. So it's in the reverse order. It's in the little endian order. So okay, where the last 4 bytes, these are the little endian representation of dead beef. So we can just view the instruction stream in an ordinary program as including both operations and certain immediate operands that the instructions can operate on. Correct. So here, what does this instruction have? It has 2 things. What is the instruction and what does it have to do? It has to move some value or something into something else. So what is the destination? EAX. What do you have to move? The immediate, basically this constant. You need to move, basically the processor needs to move this constant into EAX. So this is the instruction stream. So what they're trying to tell is this byte sequence, has 2 details. What does that instruction do? It moves stuff into EAX. Moves to EAX. What should it move? That is also present. It should move 0x dead beef. Basically the immediate. Coming back, in return oriented programming, a similar effect is possible when instruction sequences include a pop reg instruction. So we actually encountered the pop reg instruction already, so we will just go through that again, probably with a better explanation in the paper. Okay, so in return oriented programming, a similar effect is possible when instruction sequences include a pop reg instruction. For example, a pop EBX RET sequence will store the next word in the stack in EBX and advance the stack pointer past it. So that is, what do they mean by that? We will close this. So we have it here. So currently, say assume that ESP points to our pop EBX RET. So what does this pop EBX do? First, what the control is transferred to pop EBX, and then pop will pop this dummy value. I mean, here we have put a dummy value, basically any value present here, into EBX. So what they are trying to tell is they are trying to equate their we were here. They are trying to equate. They are trying to equate this with a return-oriented equivalent, basically. Return. What is the return-oriented equivalent? So how do you load something into a register or something into a location? So we saw that pop reg would work, right? Pop reg would work. But what do you need to pop into it? What value should you pop into that register? So some value here. Okay, let's say it's dead beef. So that is that. So this instruction, this byte stream is equivalent to address plus the immediate. So which is this. What was that address? 0x56555. Sorry. Let's get the address. Oh, it was some address. Sorry, I don't know. Say 350 and the. So this is equivalent to this, right? So what all information does this have? This address will point to an instruction sequence which pops value into some register. What value should we pop? This tells the dead beef. This should also this should be put on the stack too. So we can actually look at this. We can change the exploit and take a look at it again. So we will stop all this. Okay, so let us pop dead beef into it, right? Let's do that. Oops. Okay. B, let's break it func. Let's run with payload as input. Okay, the input is taken. We are here, right? Let's enter. So look at the stack. I want you to observe the stack really carefully. So first, it has a word which points to the instruction sequence pop ebx ret. Second, it has the immediate value which we need to pop into ebx. So let's go. Now pop ebx will get executed. Look at ebx. It has some value 616161, basically 4 A's, and then when you pop it, it has dead beef. So they're trying to see what is the return oriented equivalent of loading an immediate into a register, right? How is that value encoded in return oriented parlance, if I would say. Okay. So let me go over it again. So in normal programs, move eax, 0x dead beef is encoded as this. What does this instruction, what does this byte byte stream mean? So it means it has two details. One is, what does the instruction do? It is a move. Where should you move stuff into? It needs to move stuff into eax. And what should it move? It should move dead beef, the immediate. So what is the return oriented equivalent of that? The return oriented equivalent of that could be this. It's pop reg ret. How does it work? So pop reg ret and the value, they're encoded in this way on the stack. So it looks like this, basically 0x56555. Sorry, 555. What is it? 319, I think. So this points to pop reg ret and then 0x dead beef. So it's the immediate. So this is the return oriented equivalent. So this is how, what they're trying to tell is, this is the encoding of pop reg ret and the immediate. The same way move eax dead beef is encoded into this 5 bytes, this is encoded into these. So that is the idea. We can just view the instruction stream in an ordinary program as including both operations and certain immediate operands that that the instructions operate on. Correct. In return oriented programming, a similar effect is possible when the instruction sequences include a pop reg instruction. Okay. For example, a pop ebx ret sequence will store the next word on the stack. What is the next word? Dead beef. Next word on the stack in ebx and advance the stack pointer past it. Okay. So okay, there was a figure 5. Okay. Right. So look at this. This is what we were talking about. So this is the normal program thing. So it's encoded into BB, EF, BE, that one. And here, this is the return oriented equivalent. So there is a pop ebx ret, and then there is a immediate value right next to it. So that is how you do it. Okay, next comes the control flow. In ordinary programs, okay, let me drink some water. Let's see if there are any questions. Okay, so those are my friends doing some bullshit as usual. Sorry. Okay. So as of now, we know what happens when we stack up addresses, basically pointers, to multiple return ending sequences. They transfer control from one to another, and RET is the pivotal instruction. So it does the fetch and decode functioning of the processor here, and ESP always points to the next instruction or a next instruction sequence to be executed, right? That is what we know. And we also saw how encoding immediate constants in ordinary programs, the return oriented equivalent of encoding immediate constants. So we actually used it also, pop EBXRE the example. So now we look at control flow. Okay, in ordinary programs, many instructions can cause the processor to transfer control elsewhere than the current instruction sequence. These transfers can be unconditional or conditional, and they can be direct, jumping to a location determined by an immediate constant, or indirect, jumping to a location named in a memory location or a register. What do they mean? So there are different ways in x86 to jump to a certain place, right? So we are talking about control flow. Just make some white space. Okay, so there are different ways, right? So you know conditional. So basically the if else, for, you check a condition, then you think whether you need to jump or not. So say there are conditional, unconditional. What are unconditional? You simply jump to some place. Basically the goto does that. You simply jump to wherever, to whichever place specified, right? So these transfers can be unconditional or conditional, and they can be direct, jumping to a location determined by an immediate constant. So there are instructions like this, 0x 1 2 3 4 5 6 7 8, where okay, let's not do this. Let's say an address. One example would be jump 0x 1 2 3 4 5 6 7 8, right? So here this is an immediate constant which is supposed to be a valid address. You simply jump to the instruction present at this address, right? That's a direct jump. So jumping to a location determined by an immediate constant, or indirect, jumping to a location named in a memory or register. So it can also be something like this. It can be say, assuming EAX equals 0x 1 2 3 4 5 6 7 8, you can have an instruction like this: jump EAX or call EAX. This is also possible. So this is the type of indirect. Or say if you know that EAX points to, EAX is a function, okay, say EAX is the function pointer. Okay, no, let us not talk about it. It'll just make things more confusing. So this is indirect and this is direct, this is indirect. That's the word. Okay, 1 second. Regardless of their type, they operate by changing the value of the instruction pointer EIP. Correct. So when I jump to this, EIP will obviously point to this. Correct. The instruction will be located at this address. Correct. In a return oriented program, control flow is instead affected by perturbing or changing the value of the stack pointer. So we have seen that, let's go back to that fundamental question, right? How should programs be constructed if the stack pointer takes the place of instruction pointer? We sort of have a rough idea now. This is how the program would look like. So each instruction in the return oriented in a return oriented program is basically a sequence, correct? And the address is always on the stack, and the ESP always points to that instruction sequence. So ESP is the stack pointer. So the stack pointer takes the place of the instruction pointer. So ESP always points to the next instruction sequence to be executed. So we are slowly getting an answer to this question. Coming back to control flow. So control flow is instead affected by perturbing the value of the stack pointer ESP. Correct, that is true, because now ESP is our instruction pointer in ROP, right? So whatever control flow we need to change, we need to see, everything should be with respect to ESP. So that's what they're talking about. For unconditional jumps, direct jumps, for unconditional direct jumps, the instruction sequence pop ESP RET will do, if it can be found. This is a form of immediate load, as in section 4.1.3. So we will actually search for this. Before moving forward, we will search for pop ESP RET instruction, and we will see how this unconditional jump can be done in the ROP program, right? We will go back to this. Let's cut. Okay, so pop ESP is actually not there. So what we can do is, there is a gadget, there is a tool called ROP Gadget, so which actually gets all the instruction sequences present, all the return ending instruction sequences in a given executable. So we'll actually run and store it. You'll slowly understand what this is about. Okay, it will take a while. Okay, it's done. So what does this have? What does this have? So that is a question. So now we are comparing two things. This is the original obj dump, basically the disassembly of the program. This is some tool generated bunch of sequences. What is the difference? So difference is, look at instruction 4 here. Its sequence is 81 C3 33 1C 1C 0000. So here C3 is an RET. C3 is the encoding of RET instruction, right? We actually saw that. We can actually see that now too. So RASM2 RET. So C3 is the encoding of RET. So here there is an 8. There is a 6-byte instruction. Okay, but what you need to understand this can also be a return ending instruction. So there is a return instruction available at address 3A2. This is 3A1, byte number 3A1. This is byte number 3A2. So let's try disassembling and see if we can get anything useful. Okay, so that's invalid. So anyway, nevertheless, there is an RET instruction here which is going unnoticed. It's stuck in the middle of this huge instruction of 6 bytes. We actually discussed in short about this in the previous stream. Basically, you need to jump into the middle of any long instruction byte sequence, jump in the middle, and then you try to disassemble it. You might actually get some useful instruction. So here we have a good RET instruction. So let's try to jump to this instruction. Okay, so let's close this. we are here. Okay, let's come back to this later. We'll use the exploit.py and okay, we'll leave pop ebx for a while. Oops, okay, we'll use this one. So its offset is 3A1 is 81 0x81, 3A2 is this, so we will take this, copy it here. So this should point to the RET which we are talking about, right? So we will go ahead and execute it. Exploit, and we will inspect. Func run payload. Okay, so input is taken. We are exactly at oh shit, my bad. We actually had to put 3A2 here, right? 3A1 is the instruction there, so let's run. Okay, run payload. Okay, there we go. So there is RET. So what you need to understand is the compiler has generated certain instructions, right? And RET is not one of them. This RET is nowhere present here, but because we jumped in the middle of a valid Intel instruction, we found it. So there are a lot of such RETs and interesting instruction sequences hidden in the actual program. We'll actually search for it. So this was one C3. So there's one more C3 here, which is legit, which was generated by the compiler. So that's okay. Second, see, there's one more here. There's one more in the middle, right? Okay, this is legitimate. Okay, one more. Okay, oh, there's RET. There's one more. Okay, look at this. There's one more RET. Okay, so what you need to understand is 89C3 can be encoded as move EBX EAX. But what do you think 0289C3 can be encoded as? Right? We'll actually see that and see if we can get anything. 0289C3. Okay, no, it is not valid. Okay. Okay, so there are a couple of hidden return instructions. So if there are return instructions, then as the 81C3 or FF81C3 or FFF81C3, they can be valid instruction sequences which we can use. So the ROP gadget, coming back, the ROP gadget tool does that. It will identify all the hidden, interesting, useful instruction sequences, and it will dump it. So it's more useful than object dump, right? So we'll generate it again, -- binary, what is it, code1, and then code1.rop.obj. Okay. See, this has a couple of interesting things. It not only shows RET, it will list all the unconditional jumps and calls and whichever is useful to for return oriented programming. So there are, okay, so we are interested in pop ESP. This is what we are interested in. So we'll check. Okay, so there's only one pop ESP, but that is followed by an out. Okay, I don't know what out instruction does, but let's see. Out 0xFF, AL, and then call to some other this thing. So this is not actually useful. So there are, just with the sequences present in code 1, it is not possible to generate an infinite loop. So for that, what we can do is we can copy, see, the C library, the libc binary is mapped onto every single almost every single program we write, right? So we will copy that when we list the instruction sequences in libc. So we will copy cp lib32. We are working on 32-bit programs, so copy that, copy. We'll run ROP gadget not on our program but libc, which is also used by our program. That is exactly why we are using. Oops. So let's name it libc.top.obj. It will take a while because libc is a huge binary. It runs in MBs, I think. So okay, let's go back to the paper meanwhile. So we'll read this again. For unconditional direct jumps, the instruction sequence pop esp ret will do if it can be found. Correct. So okay, now we have it. J. Okay, this has a lot of. Okay, let's see what is the last. Oops, this is huge. Unique gadgets found, unique instruction sequences found, 1 2 1 2 4 3. That's huge. Okay, so now we'll search for pop esp. That's what we want, right? There are a lot of pop esps here, but there's no pop esp ret. Pop esp and then some useless, something which does not help us. Oops, sorry. Pop esp search. Okay, so we have an RET, but with it's encoded. It's the other variant of RET. So we saw in the previous stream that there are 4 variants of RET. One is the normal RET. One is the RET with stack unwind. I think this is that. Okay, let's see. Let's search. Jump to some address. Okay, pop esp XOR esi. Okay, that's fine. Pop esp CLI blah. Okay, great, awesome. So we found a pop esp RET. So that's exactly what we wanted. So we will write a nice exploit for this and look at what they're talking about, right? Okay, we'll actually do an infinite loop. We'll jump to the same instruction again and again. That'll be fun. We'll go back to the scratch pad. So we'll just write it down. Okay, now we got it, but we don't know the address of this. So it starts with add al0x8b. So this is instruction 1, this is instruction 2, this is instruction 3, and then RET. So we need only this. So we don't know the address. So we'll take this and then we'll use GDB to find the address. So that is what we'll do. Okay, so this address is helpful. That's around where pop esp is present. Code 1. Okay. Bfunc, then run, and then we need to look at where the C library is mapped, the base of the C library. See, this is the offset, but this is not the true address. So if we have the base plus offset would give the true address. So using this, we can look at the maps file of the program, and then okay, this is mapped at this. This is actually a standard address. I think we can just note it down. Libc base is this. Great. So we'll try to disassemble at X. So we'll dump 10 instructions. This plus this. I hope you are getting it. So this is the base address. It's fairly simple. This is the base address. This is the offset. So when you add the base address and the offset, you get the actual address, right? So that is what we are going to do. 0xF7DC7000 plus this. Okay, it says cannot access. Oh, okay, my bad. So there should be one more 0 here. Awesome. So okay, there is. Okay, now we are not able to see the. Let's dump about 20 bytes. We'll see what's happening. Okay, that is weird because according to where did that go? Okay. According to this ROP dot obj pop esp ret. Okay, so this is what we wanted. So this is, so there is an increment. So if we are seeing an RET here, there should be a C3 somewhere here, right? So it's okay. It's not showing. Okay, now it is present. So here is C3, and this is probably our goal. The address, right? Slash 2i. So this is, say, look at it, f7 f blah 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 6b. So this is byte 6b, this is byte 6c. So we will disassemble 6c. Okay, that is weird. Okay, we'll disassemble 6d. There is RET. What is the... Okay, then how is this pop ESP present here? That's my question. Do you have any idea? Any comments on this? No. Okay. Okay, let's search for other pop ESP. Okay, there's one more pop ESP, increment EAX. Okay, we'll try to encode this and see what byte. Let's leave this. We'll use RASM2 and then we'll encode this. We'll see what it's encoding. It's 405C C3, right? So do we see a 405C C3 here? We should be able to see 40535C C3. We'll use GDB to find. Okay, I think we need to search in the reverse order because it's stored in the reverse order. C3 5C40. Yeah, actually. So there's one here. We'll use this x/10i. There you go. This is the culprit is here. So okay, I'll just explain what we did. We didn't, I don't know why I'm not seeing any. Okay, sorry for the disturbance, background noise. I didn't see any. See, it should be this. You need to see 405C C3 here, but you just see, I'm just seeing a C3 here. Probably I'm not. So what we did is we did a reverse search. Basically we encoded this and we took the bytes. We used GDB to search where the bytes could be present. GDB is really good at such stuff, so it can help you. So here is the address of pop ESP RET. Great. So we'll use this. Where is our... With that, I think we are ready to write the exploit. Okay, we'll cut all this. What do we need to do? We need to jump to pop ESP. Give the address pop ESP. See, do you see that? I mean, we didn't find this instruction sequence in our program, but we found it in libc. That's the whole reason why the paper revolves around finding gadgets, finding instruction sequences, chaining them, basically all the sequences present in libc. So you can see that all the diagrams also mention C library. They keep telling C library because it mostly has, it's very useful, it's huge, it has a lot of unintended sequences. Okay, where do we need to pop to? Pop ESP. Where do you want to pop? Okay, let us not do anything. We'll simply execute it. Some random garbage would be popped. That's okay. That's okay. Oops. Okay, so we didn't break it from shit. Okay, you get us is done. Now we are at return. It's pointing to pop ESP as expected. We will enter here pop ESP. Some value is present. I think it's it's some value. So this value gets executed. I mean, gets popped into ESP. ESP has some value. So we will NI. So ESP is present here. ESP points this. So now, if RET gets executed, it will assume that the AAAA present here is a valid instruction, and then it will execute. But I don't think AAA is a valid instruction, so it will core dump. That is what will happen. So we'll return. So look at the EIP. EIP is interesting. So EIP should change. See, look at this. It went to some address which it doesn't exist. It's not a valid address. So we wanted to jump to that instruction itself. We want it to become an infinite loop. So what can we do? We can run this again. We can see what we can do. Okay. So how do we simulate an infinite loop here? Think about it. So we have a pop ESP. We can load any value into it, and whatever value we load, that will instruction at that value gets executed next. That is the idea. Okay. So whatever instruction sequence is pointed by ESP, that will get executed. If we want it to be an infinite loop, what should it point to? It should obviously point to this. It should keep coming back, values keep popping, and it should keep coming back to this. I think this is the value which we need to put. Where did the exploit go? Okay, I think we closed it. Okay, we'll close this, use this. Exploit, okay. Back. Okay. So where do we need to jump? Okay, there are too many of these. Give me a moment. I'll just clear them off. We don't need this. Clear. We don't need this. Clear. We sort of need all these four. Okay, so we'll go back. We want to jump back to this. How can that be done? So for that, we'll just run it once again. I just missed to note a point here. Okay, so look at this. This is very interesting. This address, this is pointing to our pop ESP instruction, right? So if ESP is always this, our pop ESP keeps getting executed. Sorry for the noise, just wait for a moment. Okay, done. So if this is ESP, pop ESP keeps getting executed. So we need ESP to be this. We need it to be this value, right? So we'll take this. We will go back to this place and then copy it. So what is this value exactly? This is the stack address where pop ESP is present. Pop ESP RET is present. We'll go back and run it, right? So if someone's following, please just don't go through the stream. I mean, it's better if you're also doing hands-on, so it'll be really you'll actually see stuff happening. It's good for understanding. So let's break at func payload. Okay, we are here, RET, right? Okay. Now we pop ESP. What is that value there? It's that old stack address where pop ESP is present. It's telling that GDB. Okay, it's telling that. We'll pop. Look at what's happening. Okay, what exactly is happening? I don't understand. Pop ESP. Okay. It seems to be like an infinite loop. Let me just do a continue. Okay, it is an infinite loop, but it's not happening whatever the way I thought it should happen. So okay, this is fine. So this is pop ESP. ESP is currently pointing to the value, the address, the stack address of which contains pop ESP. Okay. So this is popped into ESP, and then when return happens, you go back, and then you the current stack the current stack situation keeps repeating again and again. So okay, but this is sort of not clear. Why am I not able to see pop ESP getting executed, and then why am I not able to see RET? That is a question. Okay, so the idea was okay. We had to put the stack address and then pop it into ESP so that pop ESP keeps getting executed again and again and again. So that is happening. You can see that. See pop ESP, it's getting executed, but no. Okay, we'll come back to this later. Anyway, so that is how an infinite loop is, constructed. So instead of that, you can go to any place in the stack. So that's what they're trying to tell. Any place in the stack. So we can actually go to some random address. I don't know what this address does. We'll go to this address. We'll change the exploit, the payload.txt, and then we will instead of this, we will do this. So some random stack address. Okay, we'll go back, exploit, it's ready, we'll run it again, payload.txt, run. We are here, ESP. Now ESP, now the top of the stack is pointing to that random address which we were talking about. So we will pop and then return to it. See, as you popped, it actually changed. So it was some other value. So you can actually go back. It was 0xFFFF and we needed CC2C to be at ESP. So we jumped, and then now it'll return to some address here. So it is thinking this as an address, correct? So we'll try return. Oh wait, it's actually a valid. Okay. So we actually did something, I wouldn't say useful, but it didn't crash. So okay, it's something beautiful. So it didn't crash. We went to some random address which called exit in 9. Okay, that's cool. Okay, so the point to note is pop ESP can be used for unconditional jumps. See, you can put any in the exploit there. Where is that exploit? Sure. In the exploit here, you can put any random address, any random stack address, and then you can jump, right? So that was what they were trying to do. Encoding. Okay, control flow. Okay, conditional. Okay. Section 4.1.3. Okay. An example is given in figure 6. This. See, look at this. This is exactly what happened. Some random address, random stack address, and then it actually jumped to that random stack address we gave. Okay. An example is given in figure 6. Conditional and indirect jumps are more tricky, and implementing them is generally the most difficult part of instantiating a return-oriented programming environment on a new platform. Correct. So indirect jumps are basically these kind of jumps, call EAX kind of jumps. So implementing them, conditional jumps are even more difficult. See, in normal programs, let's talk about it and see why is it difficult. That's analysis we need to do. Conditional jumps. In normal programs, assembly code looks something like this. So compare EAX with 0. Okay, we'll take ECX with 0. Say ECX is some loop counter which starts from 100. It keeps decrementing every loop, and then we have a compare. So compare it with 0. So if it is true, then jump is equal to, if it is true, jump to some loop out. Basically you go out of the loop, some label there, right? So here, if they are equal, a flag is set. If they are not equal, that flag is cleared. Based on that flag, the jump will take a decision. That flag is the link between compare and jump. Right, flag is basically a bit, bool, 0 or 1. So if it is set, if it's equal, then it is set. If this is set, jump equal to will get executed. It will actually, jump to loop out. If it's not equal, it will continue in the loop. So just to complete this, it would look something like this. So you compare, and then here is the loop body, and then you decrement ECX, and then you jump to say, let's name this loop. Right, let's name loop. Jump to loop. This is how generally loops look like. So it's very simple. There's a loop. You compare with 0 first. ECX would be 100. Okay, initialization is ECX move ECX comma 100. So it will be like this, and then you enter compare. It's not 0, so this won't get executed. It will come to the loop body. The loop body will get executed, and ECX is decremented. The loop count is decremented, and then you jump back. Right? So it's a while loop. I can say, yeah, it is a while loop. It's the assembly equivalent of a while loop. Correct. So this is how conditional jumps happen in real, normal, ordinary programs. How about conditional jumps in return-oriented programs? That is what we actually need to talk about. Conditional jumps in ROP programs. return oriented programs. So whatever we try to do here, whatever compare we do, a flag is set, and that flag is useful in changing the RIP. See, let me write it out here just to be clear. Instruction pointer is modified because of the flag. Correct, right? So now instruction pointer will be this. Jump equal to may not get so it will look at the flag, and then it has two choices, either loop out or enter the loop body. Correct. So initially the instruction pointer will be pointing to loop body because it doesn't know, but then if this flag is set, then RIP is changed to loop out. That is how it will happen. How do we simulate this? How do we bring this kind of behavior in return oriented programs? These flags are useless because these flags work on IP, not ESP. And note that ESP is the instruction pointer of return oriented programs. So the flags are not so helpful in modifying ESP conditionally. If we want to do if var1 is less than var2, jump to 0x 1 2 3 4 5 6 7 8, else jump to 0x 2 3 4 5 6 7 8 9. See, what we did is this jumping is actually quite easy. We saw that. So we can use the pop ESP gadget and then do it. But how do we simulate this, the conditional part of it? How do we simulate var1, var2, and checking if they're equal, if they're greater than, or if they're less than, if var1 is less than var2, and where do we set the value, and how can that value be linked with this? Here it's automatically linked. I mean, that is how the jump instruction is implemented in the hardware. It's automatically linked with the flag set here. But here there is no link. Pop ESP is just pop ESP. It's not linked to any flag. So it's a bit tricky. It's actually given at the end of this paper. We will look into that. Okay, and implementing them is generally the most difficult part of instantiating a return-oriented programming environment on a new platform. Okay, the problem is that while processors include many branch instructions like jump equal to, jump less than, jump greater than, jump if 0, etc., these, not surprisingly, operate on the instruction pointer and are thus useless. That's what we discussed. All this revolves around the instruction pointer, the EIP register. But our EIP, the ROP EIP, is the ESP. None of these branch instructions work on ESP. That's the problem, and thus are useless. For return oriented programming, we must synthesize test and branch primitives some other way. Yes, so we need to implement the branch primitives and test. Test is basically testing if a value is less than or greater than or equal to these primitives in some other way. We need to do that. Yeah, we'll come to that. Gadgets. The techniques described so far suffice for Turing complete return oriented programming. What all did we discuss so far? We discussed encoding immediate constants, basically loading values onto certain register. If we have a pop reg RET, we should be able to, if we have that instruction sequence, we should be able to do that. Right, so moving, loading, storing values is done there. And then we spoke about control flow, basically jumping, for loops and all that. So any program you take is basically mostly that. It's data movement and control flow. I mean, yeah, I just described the general structure of a program, but yeah, that's what it is. So often, however, more than one instruction sequence will be needed to encode a logical operation. For example, loading a value from memory may require first reading its address into a register from an immediate, then reading the memory. What do they mean? So often, however, more than one instruction sequence will be needed to encode a logical operation. For example, loading a value from memory. Okay, let us leave the rest. We'll just take this, loading a value from memory. Okay, we will try doing that. Okay, loading a value to memory. How can that be done? I mean, as of now, we have a fair understanding of what an instruction sequence is and all that. So let us try doing this. How can that be done? So it may require first reading its address into a register from an immediate and then reading the memory. So in general, in a normal program, how is a value loaded into memory? It's loaded something like this. Move EAX. Suppose we need to load it into EAX. We have a D word, say EBX, where EBX has the address pointing to that D word. Correct? I hope you get the point here. This is how stuff is loaded. EBX has the address, and D word at that address is copied into EAX. This won't happen automatically. Before this, we need to load that address into EBX. Load that address into EBX. Something like this. We should have done something like this. EBX, comma, address. Say 0x12345678. Suppose if we want to read 4 bytes at the address 0x12345678, then first it should be loaded into EBX and then this. Right? So here, two primitive operations are used to load a value to memory. So we know how to load an immediate into a register, pop reg ret. So we'll try writing an exploit for that now before moving forward. That'll actually give clear up some doubts if you have. Okay, we will open. Okay, this is the libc instruction sequences. We can make use of that. Okay, that's okay. Open. Okay, what's happening? Edit anyway. Okay, I think it's open already. Okay, it's open already. Quit. We'll close this. It's here. So we will remove all this now. So this keeps changing. Our payload keeps changing because we keep trying other things out. So payload now is okay. So okay. Goal is read 4 bytes from some memory address. Right? Okay. Payload. How do we do that? First, we need to load that memory address into a register. So load. Okay, we'll just take the value of the memory address 1 2 3 4 5 6 7 8 into a register. For this, we need a pop reg. Right? So let us search for pop reg registers. There are a lot of them. So pop EAX. Hey, okay, 1 second. I think there was a pop EAX here. So we can actually take that. Okay, if we take pop EAX, say suppose we take pop EAX, then load 4 bytes into reg 2. So this was reg 1, right? So we need, okay, before this we need something like this. So pop reg 1 comma ret and then move reg 2 d word reg 1 ret. So you see what's happening. Using this, use this to load memory address into reg1, correct. Use this to access memory at that address. Access, sorry, not memory, we'll just write 4 bytes. At that address and load it into reg2. So if we find pop EA, if we use pop EAX RET, then our next instruction should look something like this: move reg2, comma d word EAX. So we have used pop EAX here. So we must search. This reg2 can be anything other than EAX, of course, but we need to search for d word EAX RET, correct. Okay, so before that we will just make note of this, and it's present at an offset, I mean in and around this. So okay, we'll close, we'll use GDB. Okay, actually we don't have to use this. We'll just close this off. For now. So we can actually use GDB to find out the addresses. So we can use the find command. So we actually search that. Oops. Okay, so before that we need to rasm2 minus d rasm2 pop EAX RET. This is what we need to search for. So let's try searching it. 0xC358. That's awesome. There are a lot of them. So libc. We'll take one of them. We'll verify. x/2i, basically 2 instructions. So we have this here. Awesome. We'll use that. Okay. Payload struct.pack little endian, the address. This is pop EAX RET. Okay, so now we need to load that memory address. So we will do that. Payload struct.pack, never miss the little endian, and then the memory address. Now the first part is done. Now we must search for something like this: move reg2 d word EAX RET. Okay, so to do this we actually need, we will use rasm. That's okay. Rasm2 move EBX, say EBX d word EAX RET. Okay, so it's encoded as 8B18C3. So we'll go back to GDB, find, always in the reverse order because it's stored in the little endian order, C318 8B. So it doesn't have anything. So there are no move EBX EAX. So we'll have to search for ECX. So it's 8B08. Let's search. Okay, so one more thing is writing an exploit it won't be straightforward. We'll have to spend time on doing all this experimenting, checking if one thing is there or not. Even I really don't know if this exists or not. If this exists, then awesome, we'll go ahead with this. If it doesn't exist, then we'll have to change the pop EAX into, say, pop EBX or ECX, whichever is available, and then go ahead. So it'll be a repetitive kind of iterative process. Can't help that. So oops, sorry. GDB, where is rasm? Okay, let's keep rasm on that side. Nope, ECX not there. EDX 8B10C3. 8B10C3. Nope. ESI 8B 30 C3 30. Nope. Okay, we just have one more thing, EDI. So if it's not present, then we'll have to do something else. Three 8. Okay, yeah. Okay, so these this is not present, right? So what we can do is we can go back to our code, our libc.rop, the instruction sequences which were there. Then we can try searching here, right? We want move say ECX comma D word PTR EAX. Okay, so we'll just search for D word EAX. Okay, 1 second. D word PTR EAX. Okay, I think the regex is messing with our search. That is what I think. This closing and opening brackets are, I think they don't mean brackets. Okay, so how do we find? Okay, searching for EX is a very inefficient method. EX. Oops. Exactly, I think it's the regex messing with the search. Okay, so that's okay. What we can do is we can. Okay, let's not use pop EX. Let's say we can use pop EBX. We'll try out certain things. Where did RASM go? Here is RASM, here is GDB, and we have pop EBX RET. Okay, great. These kind of simple gadgets are generally present in libc 5b. Whoa, a lot of them. A lot of them. So, okay, it's actually present in our code 1.2. That is. Oh yeah, pop EBX RET, yeah, it's actually present in code 1. We can actually use that. That's the first instruction sequence we explored. So okay. So now that we have changed it, we need something like this. We need reg2 EBX. Correct? So reg2 can be anything. So that's yeah. So we'll go back to RASM and quickly RASM to move EAX comma D word EBX RET 8B 03 C3. Okay, let's come out of this search. Find 0x C3 03 8B. Nope. Okay. Move EBX. Okay, no, move EBX is not a valid one here. I hope there are no bugs in RASM 2 because we are solely depending on it. C3 0B 8B. Okay. This is turning out to be really bad. I hope this is there. Okay. C3 13. Am I doing it right? C3 13 8B. Okay, yeah, that's fine. EDX is done. ESI 8BC 33 C3 33 8B. Oops. Final 3B. Nope, no luck. So they're not present. We can go back to, I wish I knew how to use Vim better so that I could, actually search without regex messing with our search. So okay, so wait a second, we can actually search it in a different manner. Move d word ptr of, say we want eax, right? Oops. Okay, let's do this. Awesome. Move d word ptr edi jump so on. So okay, we need an ret here. It's always helpful to have an ret. Wait a second. Okay, move d word ptr eax edx XOR eax eax. Oops. Okay. Pop ebx, pop esi. We actually have something, but there are a lot of unwanted stuff too. That's okay. We will make note of it. We can actually, get rid of the unwanted stuff later. Okay, we do this. Let's just make note of it. Has move. Oh, wait a second. I'm sorry. This is actually loading edx into, it's writing back. Sorry, we need to load a value. Loading a value from memory. Sorry, that's what we're trying to do. Loading a value from memory. So I'm extremely sorry. So loading a value from memory. So basically you load a value from memory to a register. So this type of thing doesn't, it's doing the other way around. So basically value in the register is being loaded onto the memory. Basically it's storing back. So that's not what we want. Okay, that's okay. We can search. Okay. No, this search obviously won't give that. Shit. I'm stupid. Okay, how do we search for it then? We'll do a random rasm2 move ebx. Okay, so this is, should I, okay, I clicked on something. How do we solve this problem? We need to search for instruction sequences, and there are a lot of them, like a huge number. More than 1 lakh instruction sequences are present here. So this is a problem. You can think about this as an exercise, which will help later. You will understand why. Okay, so I think with whatever I've done so far, move ebx comma d word. Oh, hey, wait, what? Okay, so there is a d word pointer eax. There we have an instruction sequence, but it's followed by some really unwanted stuff. So okay, we'll go ahead with this type of search. If we get something, that would be helpful. Oops. Okay, I think we missed up. Okay, move ecx. Let's just do edx. Okay, ptr esp. No, that won't help. We need it from a register. Okay, this actually can be used, but it has a jump later. So okay, wait a second. Okay, it has a d word jump from esp, but then esp would be containing okay, this can actually help, but okay, it's followed by a jump. So hey, I mean, it should not be this hard. I really don't understand what is happening. Okay. Okay, this is helpful, but there's a jump there to some random value. That's the problem. Hey, move. Okay. Do you have any suggestions as to how to search? Okay, no problem. Move EDX. EDX. Hey, well, okay, so there's okay. Move EBX comma your PDR of. Okay, there is something. Oh, this is actually okay. This is the worst case. We can actually use this. Okay. No. There are a lot of them, but they all end with jumps. Okay, return F. So the problem with this return far is that it'll return far, and this it'll mess up with the ESP. That is the whole problem. That is why I'm hesitating to use it, because it'll actually mess up with the return oriented program. Okay, let's try the other way around. Move EDX comma D word PTR EBX. Okay, it's one right. Okay. Okay. Okay, so there are a lot of pop EBXs. So it's better if we find some instruction like move reg2 comma dword ptr EBX if we can. So that's actually helpful. Okay, there are a lot of them. It's hard to search. Okay. Okay. Wait, so we are having we are spending too much time on this. We should be able to find it in some way, but I hope you get the idea. I think ROP Gadget has a ROP. We'll use this to find it. It's a good tool. It's automated. Let's see. Help. Okay. Okay. What all does it have? Okay, various architectures. That's okay. Optional arguments. Right. Binary search opcode in executable segment. This should be helpful. Okay. Only show specific instructions. Range, byte bytes, raw arc, raw Indian, offset, ROP chain, thumb. Oh, yeah, there are examples here. Okay, so we can actually search opcode. That's nice. ROP Gadget. Binary libc dot libc, and where did our RASM go? Okay, I think I'm working on the RASM window. So let's RASM2 move EBX comma D word EX IT. Let's search for this. Okay, where is it? Okay, where did that go? Opcode. Okay, opcode. This. Oh, okay, I didn't copy it properly. 8B 1A C3. Nope. that's okay. We can. So we were thinking of this, right? There are a lot of pop EBXs. So if we can find a pop, if we can find this move EDX comma D word EBX, that would be really helpful. So we couldn't find because we were doing it manually. I hope we get it. Nope, there are actually none. Okay, let's just leave this. Okay, there are a lot of them, but okay, we'll just use libc hyphen okay, should actually help in getting stuff done. Oh, okay, we should not have. Okay, this did something, but I think we can. Okay, write what where gadgets. I mean, this is the type of gadgets we want. So there is move dword ptr esi edx, and then followed by some instruction, and followed by some unwanted stuff, and then pop esi ret. Right. So okay, we found something. So here I want you to focus properly. So gadget found is move dword ptr esi edx. So ed content. Okay, here content of edx is being returned into esi. That's not what we want. We want to write. We want to read from. We need an instruction the other way around. Move edx comma dword ptr esi, something like that. Yeah. Okay, I'm surprised, but I don't. We'll have to write a program to see that. Okay, for now we'll change the goal. Okay, we'll do that. We will load a value into the memory. Basically store a value. Okay, we'll change the goal. Right, I just wanted to show. Okay, so the goal of all this was using two primitive instruction sequences to create one one operation. So to store a random value into memory, what all do you have to do? So first you need a thing something like this. You need a, say, reg1. So where reg2, you need a sequence, instruction sequence something like this, where reg2 is copied into the memory location pointed by reg1, right? And you need sequences to load address into reg1, something like this, say pop reg1 ret or something like that, or and load a random value into reg2, something similar, pop reg2 ret. So here, to store a random value into memory, which is one logical operation, we need three primitive instruction sequences. One is move dword, one is pop, and then other one is also pop. We need three. So we will search for this. Where did that go? Okay, this is here. Okay, so the ROP gadget tool actually did some work for us. Here EDX value can be stored into the ECX, into the memory pointed by ECX. If you can see properly here, see, note that there are a lot of pop EBX, pop ESI stuff too. So we'll use this. We'll just copy this down. Okay. Okay. So from what we have, reg1 is ESI, correct? So here ESI can hold the memory location because we have found such a gadget, right? And then reg2 can be edx. 2 can be edx. So now we have found a move dword ptr esi edx, but then along with that we have a lot of other instructions too in one instruction sequence: pop ebx, pop esi, pop edi, pop ebp, pop ert. So out of all these, the only useful thing is pop esi, right? So we need to store a memory address in esi, so we will do that. Okay, now we will close this. We'll start writing the exploit. Storing a value into a memory location, basically a 4-byte value. So this will include a couple of things. One is, first we need to load memory address into reg1 or esi here in our exploit case. So we'll do that. Little endian, and then where this is the offset note, we also got the libc base address before, so we can find the address of that instruction using add the base with the offset. Oops, we needed a hex of this, right? So this is where it's present. So here we have okay, I'm sorry. So first we need to load the memory into reg1. Shit. Okay. So we need to search for pop esi instruction. So here we have a pop esi instruction. So at this, it's found near this offset. So we can use GDB to find this. So x/10i offset plus, what was the memory location of libc? This, yeah. Okay, this is what is weird. I think we encountered the same problem before. So this is the offset, right? This is the offset, and we have the base address of libc. So here ideally we should have move dword pointer esi edx, pop evx, etc. here, but there is something else here. Okay, what we'll do, a reverse thing. So we'll take this, assemble it, get the machine code using rasm, and then we'll search for it in GDB. But this is an interesting problem. I don't know why the problem, but okay. Now there's GDB. We'll use the standard find 0xc3. Okay, we had to store it. So I hope you get the point. This is encoded as this. So C3 in the reverse order always, because it's stored in the reverse order. 5F 5E 0x3D. Sorry, I put double fives. 0x 5D 5F 5E. Okay, so we got them. Okay, there's one present in code 1 too, but that's great, but we'll just use a libc one. So we'll just verify. Nope. Oh, there are a lot of them. Okay, x/5i Okay, pop ESI, pop EDI, pop EBB, RET, right? Here we have the first thing we want. Oops. Pop ESI, pop EDI, pop EBP, RET. So here, okay, so now the stack needs, so when we just had pop EBX RET, we had to fill one value in the stack. We had to put one value which will get popped into EBX. But here, there are 3 of these registers. So we need to put 3 values, out of which only one is of our interest. Basically the value which goes into ESI, right? Memory address popped into ESI. Then we will just write some crap which will pop into 4, 5, 6, 7, 8, popped into EDI, and this should pop into EBB. Zero x 2 3 4 5 6 7 8 9. Okay. So here we just have one thing which loads memory into which loads the memory location into ESI. Next, 2, load the constant into what was our reg2. Reg1 is ESI, reg2 is EDX. Okay, into reg2, which is EDX. We need some pop EDX type of instructions. Pop EDX type of instruction. So let us move RASM to pop EDX RET. We should be able to find this in libc. Hopefully. Where is GDB? Okay. Find 0xC3 5A. Is it 5A, right? Yeah, C3 5A. Great. Oh, there are a couple of them. Nice. So, but see, look at these are, I think, the data values. The green are data, the red are instructions. I think so. I'm not sure. So we need to use the ones which are in the instructions, basically the text segment. We can't use the data. We can't execute, the data. So x2i. Okay, great. So this here we have pop edx ret. Payload back. What do we? Okay, address pop edx ret. So what value should we pop? We will put some random value here for now. Okay, goal is not this, it's this now. Goal is storing a value into a memory location. What value? We will store 9875. Is it? Okay, it has item, it won't overflow. Right. Value. We will write that. Struct dot back value to be written into edx. Okay, great. So now we have two sequences, the two primitive sequences which are loading a memory location into ESI and then loading a constant into reg2. Right. So now now we need to execute this. Move dword ptr esi edx. Don't worry about all this. We will come to that. Let us not use this offset. This offset is not helping us. I'll check it later, but let's use RASM. Code and then go to GDB. Okay, just search. Okay, this is a long sequence of bytes which we need to search. Find 0xC3 5D 5F 5E 5B6. Okay, I think I missed something. So C3 5D 5F 5E 5B. Okay, 1689. There is one which I think is, we'll just verify. Okay, there that is. So here we'll do that. Copy EDX, the value, into the memory location pointed by ESI. I hope you're able to understand what is happening. So payload will just be little endian, and then this is a lot. So it has move, mainly the one we are interested in is move D word ESI EDX, and then there are pop EBX ESI EDI. Okay, pop ESI, pop EDI, pop EBP RET. So now this gets executed. This is what we want, but there are 3 other unwanted instructions which we can just put random values and then get it over with. We are not concerned with that instruction, so we'll just put this itself. Copy, yank it off, then print it thrice. So you have, because you have ESI, some random value should pop into ESI, some random value pop into EDI, and then EBP. So note that the pop ESI will actually mess with the ESI register. Yes, that is true, but that will mess with it only after this is done, only after the value is written into memory. So you don't have to worry about it. So value is written and then ESI is messed up. So that is okay. We are okay with that. With that we will run. Okay, there's some problem. Should I didn't even see which line number 28. Yeah, okay. Payload. Okay, now we have a fairly huge payload. You can look at that. Till here is our, just add it again. So till here is the gap crap. From here is the actual ROP exploit, which I'm proud of. So we will go to GDB, clear it off. We'll run it with payload, right? Let's, okay, go. We are here. Okay, so you can look at the stack now. The stack is beautiful. It has a lot of important stuff here. Let's compare the stack with where did our exploit go? I wanted to compare it with the exploit. It's the same. I mean, obviously whatever is in memory is because of the exploit, but look at how the stack looks like. So the ESP currently points to a memory address which points to an instruction sequence, basically pop ESP, pop EDI, pop EVP, RET. Okay, wait a second. Okay, give me a moment. I think I should have given. Okay, just a moment. These are crap values. Let them be crap. We'll just give BB, 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 BB. Okay, so I think without saving this, I close the file. So popped into here, the BBBB is popped into first ESI, okay, and then EDI, and then EBP, right? So here we have, I think, invalid memory address 0x12345678, but that's okay. We just need to make sure we can write wherever we want. Any random address you give, if that address is valid, this would work. So we have generated the exploit again. Payload.txt. Okay, let's go ahead. Okay, we are here. Okay, now I think I'm in a better position to explain this properly, because so look at what the stack has. Look at what the authors have been trying to explain. So the stack here, we have a fairly good return oriented program. It loads a random value which we want into a random memory location. That is the idea. Here the stack has certain things. It can have memory addresses which is pointing to instruction sequence like this, like this, like this. It can have immediates like 1 2 3 5 6 7 8 BBBB, etc. So this is what they were talking about in the paper. So the stack layout, see, I'm just going through it again. A return oriented program is made up of a particular layout of the stack segment. Each return oriented instruction is a word on the stack pointing to an instruction sequence. Yes, that we saw. And it can also be, I think somewhere elsewhere they had mentioned that it can also be an immediate. So this is what we are seeing. With that, we will go ahead and execute it. So we are in the first instruction sequence. ESI is some value which we don't know, but we want the memory location 0 1 2 3 4 5 6 7 8 is the memory location to load. Okay, it is there, it is present in ESI. We load some crap to EDI and EBP, I think. Look at EDI, it is changed. Next, EBP, it is changed. Now we are about to return. Where should it return to? Right? Let's go back to our exploit. Our exploit can help us understand. It needs to return, go to pop EDX, where we load the constant into EDX. So it says pop EDX. So we are on the right track. Pop EDX. So the constant is 09876455432. Right. Correct. EDX has changed. Now ESI has the value we want. EDX has the value we want. Now we need to return to we need to return to a sequence which will load the constant which is present in EDX into the memory location pointed by ESI. That is this. Correct. So we will go ahead. You can see that move dword PTR ESI EDX. So here is where it will actually you can guess what happens. So we returned. We are about to execute. So note that ESI is the memory location, EDX is the value, and it's seg faulted. Of course, it's seg faulted because this is not a valid memory location. 1 2 3 4 5 6 7 8 is some random shitty number. So now we will put a where did that go? Now we'll put a proper value into it. Let us take some stack value. That's okay. Stack value, this, where we should be able to write. Correct. So we have taken a stack value which would be valid. Correct. So exploit will run the program again. So go ahead, take the input, pop ESI. ESI has that address which we gave. EDI has crap, EVP has crap, RET return. Okay, pop EDX, pop this value into EDX, okay, RET, return to this, correct? Here is the core. So ESI has a valid memory address. It's pointing to something. That's great. So we will go ahead and check. So now value inside EDX has been returned into the memory location pointed by ESI. So you can see that memory location is present. It's pointing to the memory location, and its value is 98765432. So we have successfully returned any constant we want. So you can look at the exploit. You can put any number here, any value here. You are in control, and then any memory location. Obviously, it needs to be valid. You can't write into a text segment. I mean, it'll segfault. So any memory address, any value, you can do that with these instruction sequences. These are crap values, which we will. Okay, there were 4, and then RET. Now we didn't actually control check what happens after after this. So there's an RET here. There's an RET. We don't know what happened, so it will crash. Yeah, it crashed. So coming back, I hope you understood what happened just there. So where were we? 1 second. We were. Okay. Often, however, more than one instruction sequence will be needed to encode a logical operation. So to write a value into the memory, to store a value into the memory, we had to use 3 primitive operations. One is the move, other is 2 pops, which loaded a memory address and a value. Basically, both are immediates, loading immediates into a particular register. Okay. So it is helpful to think that the arrangement on the stack that causes these 2 sequences to be executed as a single load gadget. Okay, this is what a gadget means. So far we have been talking about instruction sequences, chaining instruction sequences to get some work done. But here a new term has been coined, which is a gadget, and we know what a gadget is. The complete thing which is used to load, to store a value into memory is called a gadget. So we have a gadget here. So we have a gadget. We have a store anything to any memory gadget. See, note that each one of these is doing a different operation. Basically, this is popping immediate values, this is also popping, this is moving stuff, but all together they are performing one single logical operation, that is store anything to any memory. So that's you are under control of that. So this is what a gadget means. So the memory which is present here, the byte sequence, this is a gadget. So now we have all the basics we want. We know what an return ending instruction sequences. We know what chaining sequences are. We chained 3 different sequences. We chained them to perform one logical operation, which is aka a gadget. So that's some progress. Okay, that's amazing. Before moving forward, we'll see if anyone has any questions. Nope. No questions. Okay. Okay. We are at a very. I hope you. If anyone's watching, so please leave a comment below if I'm going fast or if something is not clear here. That's why I'm trying to repeat the same thing one or two times so that I make myself clear. If it's not working, so please let me know. Right. So we know what a single gadget is. Okay, we didn't do a load gadget. We did a store gadget. Basically, store anything to any memory, any value into any memory gadget. We'll continue. More generally, a gadget is an arrangement of words on the stack including one or more instruction sequence pointers and associated immediate values that encodes a logical unit. Perfect. So this is exactly what it is. So these are instruction sequence pointers. This points to this sequence. This points to this sequence. This points to this instruction sequence. And then there are a couple of immediate values which help in performing the operation. So that is what they're trying to tell. Including one or more instruction sequence pointers, there were 3 there, and associated immediate values. So these 3 are the immediate values associated with this instruction pointer. This one immediate value is the one which is associated with this. So these 3 are the immediate values associated with this instruction pointer. Okay, instruction sequence pointer, sorry, that encodes a logical unit. Gadgets act like a return-oriented instruction set and are the natural target of a return-oriented compiler's assembler. Okay, so this is we are getting to very important. We are slowly progressing towards more complex stuff. So in we have this, okay, where so let's try to understand what they told there. Okay, all this is over. So I'll be comparing X86 ISA instruction set with a return oriented programming ISA. Okay, storing a value into some memory location. In X86, how can you do that? How do you plan to do that? So in X86, it's very simple. So you move, say, ESI, comma, memory location, and then you move EDX, comma, immediate value, and then move D word ESI, comma, EDX. It's as simple as that. The compiler can use the move instructions to do this, right? But in ROP, return oriented programs, how do you plan to do that? We'll need to use 3 primitive instructions, right? So they are say load immediate to register, say RSESI load, which is basically pop ESI and anything, and then RET, and then load immediate to register EDX, that is also pop EDX, anything, it can be nothing also, RET, and then this sequence. So in X86, this is one logical unit. In ROP, this is one logical unit. And if the return oriented compiler has to store a value into a memory, it can use this logical unit directly, whatever we have found here. This logical unit can be used directly to load any value into any memory location. So this is the ISA of ROP, return oriented programs. If this is the ISA, if this is part of X86 ISA, this is part of the ROP ISA. And note that ROP ISA keeps changing. So in X86, for a 32-bit X86 say Intel processor, ISA doesn't change. It always is the same. But here ISA depends on what instruction sequences are present in libc. Here we are using libc. Say there's no access to libc, the program doesn't use libc, but it uses some other third-party library. Then we will have to find all the instruction sequences in that third-party library, and that would be the new ISA of the ROP compiler. So the ROP compiler needs to, its target instruction set keeps changing every time. So so its target instruction set can keep changing, because here in the paper they have mostly referenced the library to libc, because that is also correct, because libc is used in almost every program. But in talking practically, the ISA can actually change. If libc is not present, some other third party library, we may have to use that and generate the instruction sequence. So okay, so gadget can act like a return oriented instruction set, right, under a natural target. Perfect. Correct execution of a gadget requires the following precondition. Okay, what is that? ESP points to the first word in the gadget and the processor executes a RET instruction. Okay, we will see that. We'll go to GDB. We'll see. We actually ran it, so we know how it is. We'll just see if our return oriented program, our gadget, is following the preconditions. Okay, wait. Okay. Okay, where were we? Correct execution of a gadget requires the following precondition. ESP points to the first word in the gadget and the processor executes a RET instruction. Okay, so this is the first word in the gadget and the processor executes the RET instruction. This is the first ever, so basically this is where the func's return address was present. We have overwritten it with pop ESI's address. So this works. Each gadget then is constructed so that it satisfies the following post condition. When the RET instruction is its last instruction sequence executed, okay, when the RET instruction in its last instruction sequence is executed, ESP points to the next gadget to be executed. Okay, that is what is happening. So we execute RET. Currently, there's no RET, and ESP, basically the stack pointer, points to some immediate values, right? Immediate, okay. But then, when the processor is about to execute RET, the stack pointer is pointing to the next gadget. See? Correct? So it works. It's happening. When the RET instruction is in, okay, percentage ESP points to the next gadget to be executed. Okay. Together, these conditions guarantee that the return oriented program will execute correctly one gadget after the other. So that is what we saw. Okay. Okay, this will crash. We saw that. Okay, so that was what those are the I won't say the prerequisites, those are the basics of return oriented programming. So we saw what a return ending instruction sequences. We saw how RET does the job of fetch and encode, and we saw how instructions inside a sequence are executed. Okay, and then we saw how the post and precondition actually works. We saw this store to any memory, store any value to any memory gadget, a small program, and then we tried to do it. So that was that. Gadgets, instruction sequences, chaining them to get work done. So now we are moving to the next part, section 4.2. Have some water. Okay, so before moving to 4.2, we'll see if anyone is watching and anyone has questions. Okay, nope. Let's continue. Return oriented exploitation. A return oriented program, which we saw, is one or more gadgets arranged so that when executed, they affect the behavior the attacker intends. So you get the point, right? So a return oriented program is one or more gadgets arranged so that when executed, they affect the behavior the attacker intends. The attacker has something in his mind. So here, we as attacker, we wanted to store some value into some memory location. That is what the attacker intends. So when these gadgets were put together, this pop ESP, blah blah blah, and pop EDX and move, when these three were put together, we got what the attacker intends. So they were arranged in a particular manner, which gave what the attacker intends. The payload containing these gadgets must be placed in the memory of the program to be exploited, and the stack pointer must be redirected so that it points to the first gadget. Correct. So this is actually the place where the return address of func existed. I don't want you to get confused, that's why I'm repeating it again and again. So this is where func's return address was present, like in the actual non-attacking scenario. But now it's pointing to the first gadget. This is the first one. Okay, great. The easiest way to accomplish these tasks is by the means of a buffer overflow on the stack. Okay, as we read the paper, we just kept doing small demos, and yeah, we used a stack overflow, basically a buffer overflow on the stack, and did this. The gadgets are placed on the overflown stack, this, so that the first has overwritten the saved instruction pointer of some function. Perfect. When the function, I hope you're able to correlate what we are reading with what we have done so far. When that function tries to return, the return oriented program is executed instead. Correct. It tries to return, but these gadgets, the gadgets which we have loaded onto the stack, gets executed. However, yeah. Hey, beda. Agala. Right. Thank you. Right. Thanks.
Thank you.
That was my brother. He brought in some snacks for me. So anyway, we'll continue. The gadgets are placed on the overflown stack so that the first has overwritten the saved instruction pointer of some function. Right. When the function tries to return, the return oriented program is executed instead. So this is executed. The control is never transferred to main. Ideally, it should have gone to main, but it never goes to main. However, a stack overflow isn't necessary. So we saw that we used a buffer overflow, basically a stack overflow, but it's not necessary. The payload containing the return oriented program could be on the heap, and the attacker could trigger its execution by overwriting a function pointer with the address of a code snippet that sets ESP to the address of the first gadget and executes a return. Okay, this is interesting because they're telling that a stack overflow is not necessary. So a function pointer can also be used. So how can that be used? We will simply understand. I want you to write the program, but I'll explain clearly how it happens. So, okay, we'll actually write a program. Okay, code dot. Okay, we will remove all this. We don't need all this. Okay, I've actually forgotten how to initialize a function pointer and all that. So, shit. Okay, we'll come back to that later. I'll kind of revise stuff and then come back. However, a stack overflow isn't necessary. So, okay, so what they're trying to tell is you can store the. Okay, so idea is this. Where is the scratch pad? We can. I'll give the idea. I've understood it, but I've forgotten. Okay. How to exploit using a function pointer. Okay, so what is a function pointer? Function pointer is also a pointer, basically a memory location which has the address to a function. That's it, and nothing more, right? So and you use the function pointer to call that function. So func, say you have a func ptr is equal to and of func. So func is the actual function, func ptr is the pointer, right? And then you call, I think something like, I think it's called normally, call the function. Okay, so when the function pointer is called, it's natural, and it points, the func is executed. But what if we can overwrite func ptr with a heap address, and heap has our return oriented program. So this is, what if this is, see, this was present in the stack, right, the overflown stack, but they're telling a scenario where this can be present in a heap and we can overwrite func pointer. So when func pointer is executed, is run, our return oriented program will get executed. Okay, so now we'll just write a program to understand this explaining the concept is stupid because it's not practical and it's not helping. So okay, that's no problem. We will void star, we can Google it off. Okay, we just need a simple, very simple pointer. No fancy, nothing fancy. Okay, this is how it is. Got it. This is what we want, nothing more. Void pointer, there are no arguments, we'll initialize it and then we will declare it. Okay, should we actually, we had a func here but we removed it, so we'll just write a simple. Okay, so they are talking about overwriting this function pointer, right? How can that be done? So we will take a crafted program, right? So okay, there's some vehicle moving, some disturbance, sorry. So we will take a buffer, same. So we may not use stack overflow, we may not override the return address with this, but we will always use some kind of buffer overflow which will help us. Say 10 bytes. Okay, do this and then you take some value, right? So I'll tell you what's happening. You're initializing a buffer and then a function pointer, and then you are you declared a function pointer and then initializing it, and then let us buffer and then you're calling it func pointer. So I think this is how you call it. So you call it off. let us see if we can compile and run it. Okay, it's the same old get us problem. That's okay. We know what's the problem. It doesn't matter. Whoa, it's like faulted. Okay. See, look at what happened. Something interesting happened just right in the beginning. So this is the function. So buffer is just 10 bytes, but we gave some like more than 10 bytes. I think it's close to 20 bytes. So when function pointer is called, it's seg faulted. Why do you think it's seg faulted? Because the stack is something like this. We will wait a second. Where is the Google drawings? We will remove all this. Remove. Okay, all is done. Everything is clear. So buffer. Okay, we will remove this ESP. Not needed. Delete. Oops. No. We need to delete this. So here is our buffer. Okay. So this is the buffer. And here it's 4 bytes, 8 bytes, 10 bytes. So there will be a demarcation here. So you get the point, right? So 4 bytes, 4 bytes, 2 bytes. But you can see that I think these two will also be allocated for buffer itself. So it's called stack alignment. You can't store stuff here. So, and the function pointer, it's a pointer. So it's 4 bytes long in a 32-bit program. So the function pointer would probably be here. Arrow. God. I had to draw a straight one. Hey, arrow. Okay, something like this. So this is where the func PTR is present, right? So we will simply just so we start entering values when getAs asks for it. So 4 bytes, 4 bytes, 4 bytes, and then here is the function pointer to func, but we are overwriting it with some crap here. So we can actually write it down. WOER is present here. Okay, small, but it's 4 bytes long. So I hope you get the point. Then you come here, do it again. There is WIOE, and then you have FHOW, and OW, because demarcation is just symbolic of that the buffer stops here. And then function pointer is actually a valid address. So we can actually get the address. We'll use GDB quickly. Defunc run disas. Okay, so func disas func. So here we have the address of function. So this is was ideally it should have been that, but this is overwritten. How do I scratch this? Okay, using this. Okay, this is cool. Okay, you overwrite it with what is that? Some crap is there. EIHF. So you overwrite it with EIHF. So it's trying to jump to EIHF, which is in ASCII it will be some value. So which is mostly not a valid. It doesn't have a valid instruction in front of it. It's mostly not a valid address to. So that's why it's faulted. We will confirm this using GDB and see how we can store our program in heap and do whatever they're trying to explain there. So we'll do a demo on that. So we'll break at func. No, we'll break at main because getters is present in main. We need to go slow here. Wait, wasn't there a... I think I missed... Wait, am I... Oh shit, I'm running code 1. Sorry. We need to run code 2. I'm extremely sorry. B main run. So getters is here. We will, before entering getters, we will look at... See, currently EBX, push EDX, right? EDX, basically this is where the buffer is stored. X, say we'll dump 20 bytes. I mean 20. Oh, what did I do? Hey, I gave 20. Sorry, 20xw. Right. So this is okay. This has oh no, we'll just continue. I had something in mind. That's wrong. Okay. Okay. I'm sorry. We'll just run again. We'll enter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we kind of guessed that the first 12 bytes would be buffer and then 4 bytes would be function pointer, right? So we will try. Oops. So okay, so that's what happened. So 0xBB AABB is actually the EIP. So yeah, something, whatever we thought actually happened. So AAAA BBBB. Okay, I need to break before it. I need to break here. I need to. Okay, I need to see what's there on the return value, right? So let's break here. Run again. Okay, I think it's segfaulting before when main. Where is it? Segfaulting. Okay. 19. Okay, it's actually, yeah, it is calling func pointer and then it is segfaulting. But what I don't understand is why isn't the, oh okay, shit, okay, that's the problem, because where are we calling the function pointer? Okay, this is the call to the function pointer. I put a break pointer here, but it's useless because we need to see if this, so we'll break here, right? B, break here. So we are breaking just before the function pointer is called, nothing else. So okay. So we are just giving 10 bytes of A and 4 bytes of B. Let us see what happens. So here we are looking at call EAX. EAX has BBBB in it. So after 10 bytes, the 4 bytes are BBBB. So now we have control over the function pointer. Instead of BBBB, we can make it jump to wherever we want, right? So can we use this to bring that heap thing to reality? So we'll just read it again. I'm kind of confused. The payload containing the return oriented program could be on the heap, and the attacker could trigger its execution by overwriting the function pointer with the address of a code snippet that sets ESP to the address of the first gadget and executes the return. Okay, so this is good. So what do we want? We always want ESP to point to the first gadget, first gadget instruction, first instruction sequence. So say the instruction sequence starts at the beginning of the heap. We need to load that. So okay, where is the scratch pad? Okay. Now. Okay. So what do we need to do? We need to load load the heap address of the first gadget into ESP. Basically, ESP equals to heap address. How can we do that? That can be done. We have seen a couple of ways. We've seen move ESP, pop ESP RET. There are a bunch of instructions. So we'll go ahead and stick to that. So first we'll do that. What do we need to pop? What we need to pop? Heap address. Oh, there's a mistake here. This is heap, not head. Heap address. Right. So we need to pop the heap address, and that will do the job. That will point the ESP to the heap. But how do we store the how do we store our return oriented program in the heap? That is not told in the paper. The return oriented program could be stored on the heap, and the attacker could target its execution by overwriting a function pointer. Okay, blah blah blah. Yeah. So what they've told is, if the return oriented program is present on the heap, then we can use a simple instruction sequence like pop ESP RET, and then we can execute that return oriented program. The return oriented program, instead of being present on the stack, it is present on the heap. That's the only difference. But what we know is, we know how to write the return oriented program on the stack, because we have control of the stack. The overflown stack, we have full control over it, so we write it. But here we don't know how the return oriented program is written onto the stack. So just for the sake of it, we will okay, we'll just stop this. Code.2.c. What we will do is, before taking this, because this is a crafted program, we will only store the ROP program in the heap. Okay, so it doesn't sound really like an exploit, because obviously no program would have an intended part where an attacker can store the return the ROP program in the heap. But we'll go ahead with this. I just want to show that this is possible. It's just possible. So how do we do that? So I think car heap pt heap equals malloc of, okay, just do calloc 100 bytes of 1 unit. So we have 100 bytes all zeroed by calloc. Let's leave the error handling. It's okay. I think we want to get a null pointer there. Now we need to write, where is the exploit? Okay, now we need to, okay, leave this. Great. So now we need to put this address here. We'll just start with one address, nothing more. Okay. Okay. Wait, we'll instead of doing that, we will do this. We'll write the ROP program at the beginning of the heap. Okay, so we'll run it. So we will get the starting address of the heap. Same using the maps. Oops, sorry, code 2. Cat. Okay, we'll just go into it. Maps. Okay. So here the heap always starts from 8000 and goes till 5800 till 7. Oh, that's a lot of space. Okay, that's just address space. I don't assume that memory is backed by the address space, but that's okay. We will heap beginning, right? We'll see what happens. I mean, this is an experiment. I don't know if it will work, but we will see what happens. So now we'll write to that. So simple. Okay, we are writing by 4 bytes by 4 bytes. So we will actually take an unsigned int. That's actually more logical. Unsigned int, unsigned int. Okay. Heap equals, what value should we write? Where is the exploit? So we need to write this value. Writing here in C program is just equating stuff. So you have this here. Okay, I am the little endianness. I think it'll kind of mess with this, but that's okay. We will see. Let me reiterate what just happened. So we have written the heap address. We have written the memory address of the first instruction sequence into the heap. Where in the heap? The very beginning of the heap, right? So we know this address. This address should be the function pointer. The ESP should basically point to this address, ESP. So going back to the scratchpad, we have a value, heap address, which is this, correct? So we will do that. So the function pointer, instead of jumping to func, calling func, it needs to point to pop ESP RET. Pop ESP gets executed with ESP pointing to the first heap address. That is what we are trying to do. What does the first heap address have? It has the first address. It has the address of the first instruction sequence. If that works out, we'll obviously easily just copy this down onto the heap, but we'll just try with this before. Okay, we'll use this gcc code1.c code2.c. Oops. Okay, so that's okay. See, note how flexible C compilers are. This is an immediate value. We are typecasting it into a heap address, and that's okay. And we are doing all sorts of kind of nonsense. This type of thing should not be done in standard programs. No hard coding should be done. It should be left to the C library. It should be left to the operating system, the addresses. But here we are trying to do something kind of fancy and nice, so we are doing this. Okay, let's go ahead and run it. Okay, self-faulted. No wonder. We will break at one sec, we should break right before this, right before the call to function pointer. See, this is the call to function pointer, call EAX. We have broken before that, so we can run it. Okay, I get the problem. I'll explain this problem later, but we'll just run it once. Okay, we've broken it main. So we write the first. Okay, so it is segfaulting. Look at what's happening. It's not allowing us to write at that address. So I'll explain you what's happening. Mostly that address is present, but there is no memory behind it. So this is where address spaces and memory kind of, this is where we find that memory and address spaces are different. Just because an address is present, it's a valid address, it's an address present in a process's address space, doesn't mean there is memory backing it. It can just be a hollow address like this. This is where it's segfaulting. So this method won't work. We will have to allocate and then do it. There is no other way. We have to do that. So this won't work. But that was some try, I would say. Oops. Okay, we have to do that. We'll malloc it. No problem. Probably we'll get the same address but with memory. Malloc of 104 units each. Basically, I had to do size of unsigned int, but that's okay. Okay, so we have that. Let us be nice. Okay, we need to compile it. Okay, there's some error. Too many arguments to malloc. Shit. Okay, so it should be calloc. You know, the only difference between malloc and calloc is when you malloc 100 bytes. So here we are mallocing. Here I need 400 bytes. I'm requesting for 400 bytes. But any memory you request, malloc will simply give memory to you. It might actually contain garbage values. It may mess up with the program. That's why if you use calloc, it'll just zeroize everything. It'll initialize the whole buffer to 0, null, and then give it to you. So it's kind of clean. So okay, this should cause no problem. Standard lib or provide declaration for calloc. Okay, so it's some header file problem. That's okay. Okay, so this didn't segfault, of course, because we actually allocated memory. Sorry. We'll break at main and then run. It should be really interesting. So call to calloc is done. Okay, it gave some address. We don't know what address that is, but let us compare it with, where is the scratch pad? We can compare it with, okay, we'll just write. Didn't work. Works. So it gave an address, and then it gave an address of 160 0x160 forward of the actual heap address, where 400 bytes. We can use 400 bytes there. Ni a b, and then okay, it's segfaulted. Okay, okay, don't worry about it. So we just wrote the program now. We didn't write the whole exploit. So I don't want to, kind of mess with this exploit. So we'll just copy the same thing and we'll do it in an exploit too. We'll just put a comment saying this works on code 2. Exploit 2 works on code 2. As simple as that. So here we don't need any of this. We know that gap is 10 bytes, right? Because the buffer size is 10 bytes. And then the function pointer. So payload is that. And then the function pointer. What should the function pointer have? function pointer must point to some pop ESP RET, right? So, and we know the ESP value. ESP value is this. It should be this. Okay, I'm guessing malloc keeps allocating different values every time, different addresses. It keeps giving different addresses every time. So I just want to make sure it. If it changes, then we need to look at something else. B main run. Okay. Calloc. Okay, it's giving the same address. So okay, this is a shitty exploit, but it works. We can work with that. So pop ESP RET. So payload struct.pack. We don't know what to put here. It should point to a pop ESP RET, but we know what to pop into ESP. That is, we need to pop this heap address. It's the heap address where our program is found. Should I keep writing program? Okay, so that is clear, right? So we know, but okay, so we need to find pop ESP now. So let's get to work. I think we had actually found pop ESP, right? Yeah, nice. So it's present in libc. We'll go ahead and use libc's address. Okay, so again I'm repeating it again. Note that these addresses can be different. Whatever I am seeing, the addresses I am seeing can be different from what you are seeing if you're trying it out right now on your laptop. So the techniques are same, but the addresses can be different. So please be careful. If you copy this address or this address and try it on your laptop, it may not work because it's specific to a system, right? Okay, so now we have the stack ready, right? So we will just remove all this. It's not useful in this exploit. That is great. So we will go ahead, make it executable. Okay, great. We executed it. So cat payload. Okay, it has that. So code 2. B main run with payload.txt as input. Right. So first it'll take in function pointer is clean. It actually points to func. Later calloc enters and it gives we allocate memory and then we write stuff into it. We wrote stuff. See, look at the immediate value we used in the C program, and then we call getS. GetS will getS actually. Okay, so we made the same mistake. We need to break here. Break just before the function pointer is called. So just to see if to run with payload. Okay, make sure this we have the same address, right? getS is okay. So call EAX. Okay, so EAX should actually point to pop ESP RET, but what is it pointing to? Oh, it's actually pointing to that. Great. So I think you're able to see this. See, EAX has. Okay. Wait a second. I think we made a mistake while writing the exploit. So, okay, not here. Where is the exploit? Here. Nope. Here. So we filled the gap with 10 bytes. That's okay. And then we put this address that looks okay. But wait a second. What is this address? should have been this. Wait, didn't the exploit run properly? Okay, let's run it. Okay, oh, that is fine. Calloc, same memory address, that's great. Okay, we actually wrote at the heap, that's cool. Okay. Now EX is changed, but okay, no, that's fine. Okay, this is very weird. I need to see the stack clearly. Okay. To do this, let's start here. EBP sub ESP push EBP sub ESP 2020. It starts here. So basically I am unable to find it. I think I'm wrong with the gap here. Where is that? The gap here. The gap is wrong. So I need to find out, and wait, I have to break there. Okay, so ESP, now the stack frame is big, ESP is here, so we will say we'll look at 40 bytes WXW, the stack frame. Okay, so this is what we have, and print locals. Okay, print func PTR. Okay, it has some random value, don't worry. Print and func PTR. Where is it stored in the stack? That's what we want. So CC is 0C. So it's stored CC 000408 here. This is the place. So where is the buffer? Print buffer. Okay, print and buffer. This is the difference. This gap is what we need to consider. I think I messed up with that. Gap is this minus this. Let's see how much it is. Okay, it's 14 bytes. Shit. Sorry. So, okay, so I think now we are clear on this. Oops. We have run the exploit. Payload.txt. Great. We will completely focus on this now. Okay, memory allocated. Same address. Okay. Okay. Okay, something's okay. This is fine. Get us. We got the. Oops. I think we just crossed this one. We'll just break before the function pointer. Sure. Okay. Now we are here. What does EBP minus 0xC have? Okay. Go ahead. What does EAX have? Okay. Now EAX is pointing to pop ESP. Okay. Now it's correct. So the exploit. So the gap was wrong. It was 14 bytes. I was just taking it as 10 bytes. So now it's okay. Now we are call EAX. So we will step into it, Perfect. So look at it. Now pop ESP, but some random value is present here, but the value which should be present here is this. Oh, this is actually even more a bit complex than what I thought. Okay, so we are not, so there is a call to a function here. So if you look at it, okay, I got the mistake which I'm doing. So here we are calling it. So when you call it, two things happen. One is you jump to this address and then you pop this off. Okay, no. One is you pop this and jump to it. And what about the stack here? Okay, so because this is a call and not an RET, I think we need to okay, let me be clear. So there was a call to pop ESP RET instead of a return or a jump. So when there is a call to anything, it always expects a return address. So we will give a crappy return address. We encountered the exact same problem when we were writing the return to libc exploit. So there we had to do something like this. So if there was so there we called, we had to put a no, this isn't sounding right. No, okay, we'll just try with this. A dummy return address. Okay, continue. Now we are almost there. We'll step into it. Okay, even now it's the same. So what are we missing? Okay, so it's not as straightforward because okay. I think I got the mistake. So when there is a call to any instruction, when there is a call to a function, what happens is, great, this is good learning, this is amazing. So when there is a call to some instruction or function, the next return address is pushed. So that's what is happening. So it pushed this. So if we let's run it again and we'll exactly see what I'm trying to tell. So here, see, look at the stack. Okay, so here we are just about to call this, assuming it's a function. We need to call it. So we'll go ahead. Excuse me. We'll go ahead and call it. And note that this is the return address. Once this call is done, we need to return back. I mean, we won't be returning back, but see, once this call is done, this is the return address which will be pushed. So let's go ahead and step into it. See, it was pushed. It was pushed here, right? So go ahead and when you return, oh, there's some issue. So obviously it won't return naturally. So that's okay. So that's the problem. It's pushing, it's messing with our ESP, this thing. So what can we do about that? So let's go to our exploit. Where is, okay, it's useless. how do we, so okay, we'll start here. We are calling it. Once we call it, suddenly there is some return address which is messing up. Okay, we'll write it here in the scratch pad. Okay, so because it's a call EAX, return address is pushed onto stack. So when it's pushed, everything is messed up there. So what we need is, we just don't need a pop ESP. We need a pop, say pop some reg1, pop ESP RET. So here what can happen is, when the first pop reg1 gets executed, where is it? Pop reg1 gets executed. When pop reg1 gets executed, this return value is popped off, and then when pop ESP gets executed, the actual value which we want ESP to be, which is this, gets popped into ESP. So okay, we didn't need that dummy address. I'm just trying out stuff here. Okay, we need to get this exploit right. Come on. Okay, does anyone have any suggestions? Nope. Great. So let's continue. Pop ESP RET heap address where, okay, ROP is found. That's all fine. But one thing is, I don't see this value in the stack. That's what I'm. It's kind of a problem, right? Okay. Just go on. Okay, the address is the same. Okay, getters is. Oh wait. Okay, we need to break. Done. Okay, we'll just break here. Run with the payload always. Just continue. Right. So here. Oh. Wait a second. I think I know the problem here. This add ESP is messing with our stack because it's changing ESP. Damn. Okay. So we will see what we can do here. Should executing stuff on heap, I mean putting ROP on heap and doing this is actually taking some time. That's okay. Just Okay. Memory is over. Done. Got to get us NI. Okay. So now we had to break here. Okay. It shouldn't go there. Break there. Perfect. Before add, how does the stack look like? That's what we want. So print buffer. Okay, print function ptr. Perfect, that's cool. But print and we need to look at the complete picture. So let's just dump 20 D words. Okay, so we have 61 AA 61, and then here is the return address. So basically F7EF DF56, and then there is 56788160. So that this is okay, the stack looks exactly the way we wanted it, but it's not working because what is the ESP value? BE0. Okay, from 30XW CBE0. Okay, so here looks fine. So it starts from here, the buffer CCAA, and then the return address, I mean the address to pop ESI, and then okay, we didn't, okay, that's fine. So it looks like this. But then when the add ESP 0x10 is executed, the ESP which is pointing here start points to here. It points to, we'll execute that. It's done, right? Now we will say dump 20XW $ESP. Okay. Move EAX dword PTR EBP minus 0xC. Okay, what is present? That will also work, because we know it, so that is fine. Okay, so the top of stack is different. When you're calling a function pointer, this is the top of the stack which needs to be set. Damn. Okay, so I think we should make a list of what all we need to visit later. We'll take this up later, make sure we get this exploit. Things to visit. Heap, ROP on heap, and NOP Sled, and we also had mitigations, which will come to. If there's anything left, we'll add on to that. We'll continue with the paper right now. Yeah, I hope you get the point. So we somehow wrote the program onto the heap, and then we are now trying to point ESP to the heap, and I'm unable to do that currently. So we'll do that. Okay, we note that the gadgets that make up a return-oriented program need not all be placed contiguously in a single payload. By means of control flow gadgets, an attacker can transfer control from a small first stage on the stack to a larger second stage payload on the heap. Man, this is okay. So now they're taking it to the next level. So if there's not enough space on the stack or something like that, they're suggesting a way out. So you can put some stuff on the stack, and then once it's executed, you set up, and then you jump off to the heap. You make ESP point to the heap, and then there it's the second stage. So this is good. We need to try all this. We need to come up with exploits to demo all this. It will be really cool. 2-stage stack heap ROP exploit. Okay, this is cool. We note that gadgets that make up blah blah. Okay, indeed, the first stage could read in the second stage payload over the network, as in the Metasploit project's multi-stage exploits. Okay, so Metasploit is the amazing attack project. It has lots of tools, lots of exploits for tons of vulnerabilities out there. So okay, same time. So this is amazing. I'll just take a moment to talk about it. It's a pen testing network. It has a lot of exploits on Windows, Mac OS, and Linux, and it's too good. You need to look into it. Yeah. Okay, so we were sort of partially successful and we didn't succeed completely with the heap. We'll come back. Finding useful instruction sequences. The building blocks for the traditional return into libc attacks are functions, as we saw, system exec, exit, etc. And these can be removed by the maintainers of libc or other target library or binary. So that's what we were talking about. So for WXORX to be completely effective, completely resistant of return into libc, what we can do is, first, as defenders, first employ WXORX throughout. Second, remove all the functions which help the attacker, such as exec, libc, system, etc. So without them, the attacker wouldn't probably do anything. So that's the idea. By contrast, the building blocks for our attack are short code sequences. We saw that, each typically 2 to 5 instructions long. Every instruction sequence that ends in a RET is potentially useful. May or may not be useful, and we have seen that if it ends in RET, it can be useful. In this section, we discuss how an attacker can enumerate the available instruction sequences in order to construct gadgets. Right. Okay, so there is a note here. In fact, there are other possible combinators. For example, if %EBP points to RET instruction in libc, then any sequence ending in jump EBP can also be used. Correct. So it doesn't have to be an RET. If EBP or EAX has a valid address in the libc or to any other useful instruction sequence, we can as well use that. Okay, so in fact we can, if we consider code 2 as this as main, code 2, here there is a call EAX sequence. Somehow if we can load EAX with some the required address and then call, we should be able to go to that address. Okay, that's actually what we are doing. We are doing what exactly they've told here. Okay. Oops. Okay. Intended instruction sequences. Every instruction sequence ending in an RET, ending in a return instruction, RET on x86, and the return RET restore sequence on Spark is potentially useful. One obvious source of such sequences is function suffixes and exits in a target library like libc. Correct. So function suffixes are basically the epilogues, the endings where we saw pop EBP, leave pop EBP or leave RET, instruction sequence. In any target corpus of any platform, there will be many such terminations. We simply backtrack from these returns and examine the preceding instructions for useful functional bits. What do they mean by that? Let us take an example. Let us look at, okay, let us actually get the ops dump of libc libc.ops dump. It will take some time. Okay, great. So what they're trying to tell is, take any function suffix. So we'll search for RET. So this is okay, it doesn't look like a function suffix. We'll search for leave. This is definitely a function suffix, looks like that. So a leave, you take it, and then we simply backtrack from these returns and examine the preceding instructions for useful functional bits. So you start with C3, right? So okay, we can use RASM here. RASM is extremely helpful in such like short symbol situations. RASM 2 minus, we need to disassemble it. So we start with C3, right? RET, we know that. We backtrack by 1 byte. We take C9, right? We know that. Now we don't backtrack by 3 more bytes, but we backtrack by 1 byte. And we know the reason here. I mean, the the density of the x86 encoding is very high, and we may find a useful instruction here. Okay, so CLD, I don't know what CLD does, but it looks like a valid instruction, so that's useful. Now let's take 5D. That's amazing. So we have a pop EBP, CLD, leave RET. Okay. And now if we take 8B, then we know what we get. We'll get move EBX and the sequence which is generated by the compiler. That is cool. We'll backtrack a little bit. 09. Okay, we got a totally mostly useless sequence because there's no RET present. 7-4. Okay, that is something. Jump if equal to 0xb. I don't know if it's useful. Let's go on. So we can keep backtracking and check for useful sequences. So this is not the only useful sequence. So RET in itself, where is that? RET in itself is a useful sequence. Leave RET can be useful. Move, these natural sequences, instructions which are generated by the compiler can be useful, but there are also unintended instructions like these. Pop EBP, CLD, like CLD, leave RET. You never know where you can use CLD, right? We don't know what it is, but we may use. Pop EBP, CLD, leave RET. So that is what they're trying to say. You start with a return and then backtrack byte by byte and see if you can get something meaningful, something interesting. On CISC platforms such as the X86, where instructions are variable length and unaligned, we can in addition use unintended instruction sequences discussed in section 4.3.2. We have kind of gone over it a lot of times here. We'll just go over it one more time. We'll look at an unintended return. Exactly, we got an unintended return here, so we will use that. We know RET is useful. Okay, we then backtrack and take 8.3. We'll see if it's useful. Where is 8.3? Okay, no, it's invalid. No problem. D4. Okay, that is, we got some valid instruction. AAM, I think it's a variant of addition, or it's an ASCII instruction, not sure. So 4D. Okay, there's a decrement EBP and AAM 0x83. 4D 8B. Okay, so here we got something. So there is an instruction which moves some memory, some value present at the memory EBP minus 0x2C into ECX. Can be helpful. Oh, but there's an invalid instruction in the middle. Okay, this should not, this kind of thing should not be generated by RASM. If there's an invalid instruction, then I think it should stop here, right? It should not go till RET. Okay, that's okay, I think. Get the point. Oh, it's totally, oh no, wait a second. Okay, that's not useful. C4. Nope, not useful. Okay, now to do this. 1-0. Okay, so basically that is the idea. So you jump at some return in the middle in the text segment, strictly text segment, and then you backtrack byte by byte in a hope to get some useful sequence. See, that can only be done in x86. In Spark, that cannot be done because it's aligned. The instructions are aligned and it provides only aligned memory access. You can't access in the middle bytes and all that. So that's how it is. By contrast, the Spark platform restricts 32-bit instructions to a 4-byte width and enforces alignment on instruction read, preventing us from using unintended instructions. Great. Okay. We carry out experiments on the standard Sun provided Solaris C library version blah blah blah. Our testing environment was a Sun Spark server running Solaris 10 with a kernel version string so and so. Our search relies on static code analysis with the help of some Python scripts like ROP Gadget, which we used, of the disassembled Solaris libc. Okay, so first they disassembled and then they started searching for it. Okay, the library, which is around 1.3 megabytes in size, contains over 400 return restore terminations, each of which potentially ends a useful instruction sequence. We examine each of these returns and work backwards, cataloging, or fancy way of listing, I think, listing the useful computations we find along the way. See, that was about Spark, and now okay, unintended instruction sequences. The second option for finding returns available on architectures like the X86, where instructions are variable length and unaligned, is to look beyond the instructions placed by the compiler or assembler and consider returns found by jumping into the middle of existing instructions. So we have seen it. So this is some instruction, add ebx, 0x4, and it's encoded into 3 bytes, and this is exactly the middle of that existing instruction. So that's what they're talking about. Here is a concrete example of such unintended instructions on the X86 taken from our testbed X86 libc. 2 instructions in the entry point ECB crypt are encoded as follows. Okay, I think this is a libc function. I think so. So they have something here. Because of the density, okay, they have an instruction sequence, basically these two, and then because of the density of the X86 ISA, it is quite easy to find not just unintended instruction sequences, but entire unintended sequence of instructions. So what they're telling is, you just not only find one unintended instructions, but unintended sequence of instructions. So this whole is a sequence. This, okay, I'll just take an example. We'll take this. We'll use RASM. See exactly what they're trying to do. Disassemble. Oops. Copy. Okay. Yo. Okay, sorry about that. Okay, so here we have some couple of bytes, and then it's can be disassembled to test EDI 7. Basically this is in the AT&T syntax. This is what we are seeing on the left hand side. Your left hand, okay, yeah, left hand side is Intel syntax, don't worry about it, and set an ZB, and it's some instruction. But if we remove F7 here, look at it, magic. So you get like a series of sequence. So RET is definitely an useful one. Increment EBP RET can be useful. Exchange EAX RBP increment. So this is one. So I'll just list out all the interesting sequences we get here. List. Okay, we'll just come off this. List of all. RET is just it. A sequence can have one element, that is totally valid. Okay, this is one more. EXHG, basically exchange. EAX EBP, increment EBP RET, and then we have, just copy it for the sake of fastness. Copy it. So we have 4 instruction sequences here just by removing 1 byte from the disassembly, from the byte stream. So this was the original byte stream, F7, C7, 0700, blah blah blah. But then we removed F7 and then we got a couple of interesting sequences. So that is what they are trying to tell. Because of the density of the X86 ISA, it is quite easy to find not just unintended instructions, but entire unintended sequences of instructions. These sequences must end in a RET instruction represented by the byte C3. Great. So we carry out our experiments on the GNU C library distributed with Fedora core release for libc 2.3.5.so. I think my laptop, this version is 2.27. Okay, and it's Ubuntu. Our testing environment was a Pentium 4 running Fedora core release 4. Okay, a Linux kernel version 2.6.14. Whoa, that was pretty old. My oops. Nope. I think my this thing. Oh, okay, kernel version minus V. Sorry. It's using kernel version. Oh, that is. It needs to tell the kernel version. Okay, minus R. Okay, it's using 5.3.0, so that's pretty new. That's okay. But we are running 32-bit programs on this, so it shouldn't be much of a difference. Okay, the gadget catalog we give in section 5 uses only unintended sequences, those that begin in the middle of a real instruction end with a RET, but whose terminating RET may or may not be unintended. Okay. So I want you to understand each and every word here. That is the whole point. Okay. So this demonstrates the power of unintended instruction sequences. Also, considering intended instruction sequences as in section 5.3.4.3.1 would only increase an attacker's power. Two observations guide us in the choice of a data structure in which to record our findings. First, any suffix of an instruction sequence is also a useful instruction sequence. If, for example, we discover the sequence A, B, C, RET, A is an A, B, and C are instructions in libc, then the sequence B, C, RET may of course also exist. So, where the scratch pad, we actually just wrote something like that. So, taking this, here move here A is this, oops, A is this, B is exchange EAX EVP, C is increment EBP, and then of course we have the RET. So we found a sequence like this A, B, C, RET, but it also means that B, C, RET can also exist. It actually exists. Also C, RET can also exist. It exists in this case. So they can also be useful. Not only this one sequence, but this sequence, and this sequence can also be useful. So that's what they're telling. Second, it does not matter to us how often some sequence occurs, only that it does. So if the sequence occurs, okay, what does that mean? Second, it does not matter to us how often some sequence occurs, only that it does. From the occurrences of a sequence, we might prefer to use one of which. Okay, so consider an instruction sequence like this: pop EBX RET. It doesn't matter how many times pop EBX RET occurs in the program, in the address space. So what it means is, let us go back to, I just want to make you understand that. So we break at main say, so we'll find, where is RASM? Okay, something is actually running here. We will come out of it. RASM to pop EBX RET. C3 5B. Great. So find 0x C3 5B. So there are a lot of pop EBX RETs in the complete address space. Code 2 in itself has 2 of them, and libc has a bunch of them. Okay, a lot of them. Look at this. libc just has a lot of them, 257 of them. So it doesn't matter how many times it occurs. Even if there's one, that's more than enough. That's more than enough to load a value into EBX. So it doesn't matter how many times it occurs, just that it occurs. It matters only that it is present. Doesn't matter how many times it's present. So that is what they mean. Based on these observations, we choose to record sequences in a trie. Okay, this is interesting. Trie is a simple, very simple data structure, which looks something like this. We'll go for a drawing here. File, new, drawing. Oh, it's perfect. So a trie, okay, we'll just read on and then construct it. Where was it? Trie. At the end of, at the root of the trie is a node representing the RET. Okay, so we will use circle and then a text inside it. RET C3. Okay, that's cool. And then we have one more. Okay. At the root of the trie is the RET instruction. The child of relation in the trie means that the child instruction immediately precedes the parent instruction at least once in libc. So we will draw an arrow and this. Well, I actually don't need this. Just delete it. Here we can actually store one more. Scratchpad. Okay, we can. So C is increment EBP. Great. Increment EBP, which is some machine code. Okay, so after that there's one more. I need to use the arrow. There's one more which will, okay, we'll just read on. Pop child of relation at least once in libc. Okay, for example, if in a trie a node represents pop EAX is a child of the root node representing RET, we can deduce that we have discovered somewhere in libc the sequence pop EAX RET. Great. So that's exactly what it is. So this is there, and then increment EBP, and then not only that, we actually have more. We have exchange EAX EBP. Great. So text somewhere here, and it doesn't stop there. We have more in this particular example. Let me draw a smaller chotu circle. Okay, like a broader one. So, and we have the biggie, which is this. I hope you get the point. So each of these arrows signifies a child of, child of relation. Okay, so let me start over again. RET is present. Give me a moment. for that. Where would we? So explaining it again. So we start with RET. So look at it as backtracking the whatever we did. So we start with RET, we backtrack by a byte, and then we find increment, and then we make it this is the try. So and we make the child of RET is this, and then this has one more child of, this has one more child. So this is a very efficient way to store four instruction sequences. RET in itself is a sequence. RET, and then you dereference this child of, and then you get one more sequence which is increment EBP RET. You dereference one more child of, you get exchange EAX EBP, that is one, increment EBP RET, that's one sequence, and then you dereference it again, you get full, all the four instructions being in one particular sequence. So that is a try. So a try is, the name try is derived from the word retrieval. So where is the scratch pad? So it's this retrieval. So yeah. So I hope you get the point. So our algorithm for populating the try makes use of the following fact. It is easier to scan backwards from an already found sequence than to disassemble forwards from every position, every possible location in the hope of finding a sequence of instructions ending in an RET. I mean, that's fair, man. See, look at how big libc is. It's huge. So you can't keep disassembling at each and every point possible in a hope that you would get an RET instruction. You would get a sequence ending with an RET instruction. Instead, you deterministically parse through the machine code. You parse through the machine code. Say we are kind of parsing here. We are moving this, and we get some C3, which when disassembled gives RET. Once you get it, you move backwards. You move C3, and then you do 83C3, D4 83C3, 4D D4 83C3, B4 4D D4 83C3. So you move backward. You get it in a deterministic way, and then you move backward. And move backwards from an already found sequence than to disassemble forwards. That makes sense. When scanning backwards, the sequence so far forms the suffix for all the sequences we discover. The sequences all start at the instances of RET, correct, which we can scan libc sequentially to find. That is simple. It's just a single pass. So you start with just go to 0. You start with, where's the text? It's here. This is the first byte. You start here, and then keep moving. You parse, comparing every byte with C3, C3, C3. Oh, suddenly there is a C3. You stop there, you disassemble it. So we'll just, we'll do like a manual thing. Just a moment. I want you to get the complete, like a clear picture of what's happening. RASM2 minus D. You're moving. Okay. Now we wanted this. Yeah. You start from the first byte. 57 not C3. 56 not C3. 53 not C3. Move. 81 not C3. C3, yes, it is a C3. So you go there, and then you disassemble it. Okay, that is like, we know that. And then you move one byte backward. Okay, it's invalid. That's okay. That doesn't fall under the try. Note that it doesn't fall under the try. 0081 C3. Nope. Okay, this is something. C6. Okay, still we have a couple of invalid instructions. It might actually contain invalid instructions. Can't really help. So this is a lone return which is, just lying there. So that can happen. But there can be return which when we backwardly when we disassemble each byte moving backwards, we can actually get a valid instruction sequence. That is also possible. So that was about that. In looking backwards from some section, we must ask, does the single byte immediately preceding our sequence represent a valid 1 byte instruction? Do the 2 bytes immediately preceding our sequence represent a valid 2 byte instruction, and so on, up to the maximum length of a valid X86 instruction. So valid X86 instruction, like a 32-bit instruction, is 12 bytes. So we can go to 12, we can go, this is 1, 2, 3, 4, 5, 6, 7, 8, and move. Any answer, any such question answered yes gives a new useful sequence, of which our sequence so far is a suffix, and which we should explore recursively by means of the same approach because of the density of the x86 ISA. More than one of these questions can simultaneously have a yes answer. Okay. We present our algorithm in pseudocode in section A.1 in the web only appendix. Okay, it's present in at the end of the paper, I think. So, that was section 4. Man, I think we spent 11 to 12, 12 to 1, 1 to 2, 2 to 3. Shit, we spent 4 hours on section 12. I mean, that was the introduction of return-oriented programming. I mean, we did waste some time on spending on the heap problem and all that. But I hope you get section 4. That is this section explains what return-oriented programming is. So we also looked at a couple of gadgets. We know what a gadget is. We know how a logical unit of operation is constructed using several instruction sequences, and we have seen that a stack return-oriented program, basically it's a series of words where each word can point to instruction sequence, or it can be an immediate associated with an instruction sequence. That is sort of clear now. We know how a return-oriented program looks like. So, and now coming back to this question, how should programs be constructed if the stack pointer takes the place of the instruction pointer? This question, I think we sort of have an answer for that. The program looks like a series of words. That's what we explained, and each word can be a point to an instruction sequence or an immediate, and the stack pointer will always point to an instruction sequence, and mainly the decode and fetch and decode operation will be done by the RET instruction ending at the end of every instruction sequence. This is a key point. That is how a program would look like. The program would be a chain of instruction sequences with each instruction sequence ending with an RET. That is how the program would look like. So I think we have I hope you understood each and every of these figures. They show something significant, so we have gone through that. Okay, finding. Okay, now coming to the I can say it's not the last section, but last main section. Probably will end our stream with this section. Okay, X86 Gadget Catalog. Okay, so before we start, we'll just take a small break and then come back. Yeah, great. Show log. I think I screwed up. So I'll start again. I think I had not switched on the mic, so let's start again. In this section we describe our catalog of gadgets on the, sorry for the noise, gadgets on the X86 platform. All the instruction sequences we use below were found by our algorithm when run on our test libc. Great. Note that we rejected some sequences because they were, just want to make sure, okay, nice. Note that we rejected some sequences because they were intended suffixes of libc functions. We did that to prove that the availability of a Turing complete gadget set is not an artifact, or I can say an implication of particular functions in our test libc. A real attacker would obviously not reject such sequences and would have an easier time than we did. Great. The set of gadgets we describe is Turing complete by inspection, so return oriented programs can do anything possible with x86 code. We stress that the code sequences pointed by our gadgets are actually contained in our target libc. They are not injected with the gadgets themselves. That is ruled out by WXRX. So I think by this time you should, you should have understood, like you should be able to understand what they are trying to tell. So we didn't inject anything, any code into the program. Yes, we did inject addresses. We did inject immediate values. Yes, but we didn't inject any code and run it because it's just not possible. So all we did was we injected addresses which pointed to code sequences already present in libc or the program itself. So that's not harmful. I mean, that from our point of view. So WXRX won't harm us. So 5.1, load or store. We consider three cases: loading a constant into a register, loading the contents of a memory location into a register, and writing the contents of a register into a memory location. Okay, so that is load store. Three types. We'll see what those three types are. Loading a constant. The first of these can trivially be accomplished using a sequence of the form pop reg ret. So load immediate into register. We can use exactly pop reg ret. We have already seen that, so there is no issue. Second, okay, we'll continue. One such example is illustrated in figure number 8. Figure 8. So let's zoom in. Okay, this is figure number 8. So this is what we did. So the ESP was pointing here, and then the address is there, and then this is the immediate value associated with this instruction sequence. So that should be clear by now. In this figure, as in all the following, the entries in the ladder represent words on the stack. Okay, so these are all 4 bytes, it's basically this. Where did the other thing go? It's basically this, nothing else. All words on the stack. Represent words on the stack. Those with larger addresses are placed further down on the page. Some words on the stack will contain address of a sequence in libc. Our notation, somewhere correct. Our notation for this shows a pointer from the word to the sequence. Okay, correct. Other words will contain pointers to other words or immediate values. Okay, yeah. Loading. So what they're basically telling is, so look at this. So this is a pointer. Figure 9. I'm showing figure 9. This is a pointer to an instruction sequence, and then the next it points to some other memory location, and then here In figure 8, this is an immediate value. So there are 3 types which can be present on the stack. So loading, so you got the point, right? So this is loading a constant into a register is cakewalk. It's nothing. Then loading from memory. We choose to load from memory into the register EAX using the sequence move L64 of EAX, EAX RET. So this is nothing but loading from memory. This is nothing but move EAX D word of EAX plus 0x64 or only 64 again. It's not hex. So this is on the right hand side. This is the Intel syntax equivalent of whatever is given here. Okay. So move EAX. So that's okay. We first load the address into EAX. Yeah. I think we encountered this problem. Okay. Sorry. We encountered this problem earlier. So for this won't work automatically. The first address should be loaded into EAX. How do we do that? Use pop EAX RET. That's it. Simple. And you know which address needs to be loaded into EAX. So address is also one more kind of immediate. It's nothing special. Just that it's a number. It's an immediate which is an address. It's an immediate. So you can use pop EAX. Right? Once you do pop EAX, then move EAX, D word EAX plus 64 RET is not a problem at all. So that is cool. Next comes Next comes. Okay, just read on. We first load the address into EAX. Because the immediate offset in the move instruction we use, the address in EAX must actually be 64 bytes less than the address we wish to load. Correct. So here we have some gadget. Okay, so we'll continue. We'll understand this completely. So we need to read from memory 0x12345678. Okay. Now basically need to read 4 bytes from memory, so and so. You will pop, what address do you pop into EAX? So we need to read from this. So EAX plus 64 should be equal to 0x12345678, which implies EAX should be EAX should be memory location, which is minus 64. That's what they're telling. So EAX, value of EAX should be 64 bytes less than the memory location. So when it is loaded, EAX plus 64 is computed and you will get the memory location back. So that is how it's done. Okay, so this is sort of clear. Because of the immediate offset, okay, that's done. We then apply the move sequence, after which EAX contains the contents of the memory location. That is correct. So we'll read and it is read into EAX itself. Or it is something like this. So this kind of code is not allowed in C, but I'll just write it. EAX is equal to star EAX. So if you just have a unsigned int EAX, because it is 4 bytes, it can be used. It represents 4 bytes unsigned int. It can also have an address. So it is actually doing this instruction or something like that. It's basically loading memory. You're loading 4 bytes at this memory address into the same variable itself. So that is possible. Oops. Things to visit, that's for later. Continue. Oh, wait a second. The procedure is detailed in figure number 9. Note that we use to signify the pointer in this cell requires that 64 be added to it so that it points to some other cell. Okay, see, look at this. 64 be added, it'll point to some other cell. Okay, it doesn't actually have to point to stack itself. So here they're trying to, the pointer is pointing to the stack, but it can be anything. It can be heap. You can actually read from text also if for some reason you need to read, or the read only segment, doesn't matter. Any place where you can read from. That's, I think, the whole program memory layout. So that's peaceful. Okay, now storing to memory. We use the sequence move L EAX24 EDX RET to store the contents of EAX into memory. So we load the address to be written into EDX using the constant load procedure above. See, we actually did a load, we actually properly demonstrated storing to memory thing. So storing to memory logical unit. So coming back, storing to memory. So here we used, I mean, here they have given an example, no problems, but we actually used okay, now we need one more window. Exploit has stuff in it. So we actually used this sequence, move dword ESI. So ESI and EDX are the two registers we used. Here they're using, I mean, they found a gadget with EAX and EDX, but we used a gadget with ESI and EDX. There's no hard and fast rule here. Use whichever is available. So that's I hope you have understood the storing to memory properly. So in short, you need to have something like this. Move say d word reg1 comma reg2 ret. Before that, you need to pop reg1 ret, pop reg1 ret, the memory location, pop reg2 ret, the immediate value. These two are very important. So it's sequence of 3 instruction sequences. So you can tell that they are arranged in particular manner to get the thing done. Okay. The procedure is detailed in figure number 10. You can actually understand this. It's fairly simple. We have actually implemented it, so it shouldn't be hard for you to understand. Arithmetic and logic. There are many approaches by which we could implement arithmetic and logical operations. The one that works best for our instruction sequences available in our libc is as follows. Other gadget sequences on the X86 have used different approaches. For all operations, one operand is EAX. This is what they're trying to do. This is what their standard gadget catalog has. The other is a memory location. Okay, depending on what is more convenient, either EAX or the memory location receives the computed value. Okay, this approach allows us to compute memory to memory operations in a simple way. We load one of the operands into EAX using the load from memory methods. Correct, using this load from memory. We apply the operation, basically the arithmetic operation, add, XOR, whatever operation, and if the result is now held in EAX, we write it to memory using the store to memory methods. Peaceful. I mean, that's mostly what you need. You load something from memory, compute something, and store it back. So that's convenient. Add. The most convenient available sequence is the following: add L, EDX, EAX, push EDI, RET. Okay, so we are out of load store here. We are into arithmetic and logic, and in that add. Okay, they have found a add d word, add EAX, comma d word of EDX, comma push EDI, RET. Okay, so this is the one which gets the work done. So EAX has some immediate value, EDX has a memory location, and those two are added, the value present at that memory location is added with EAX and stored in EAX itself. So I mean, you know that it's something like this: EAX equals EAX plus star EDX. Basically, it's more like this. I'm saying int star EDX. Different. EDX is basically a memory location, right? So, so you're dereferencing EDX, and it's a D word. D is a double word, that's 4 bytes. It's signified by unsigned int. So this is what's happening. And push EDI is a sequence which is, I think it's not useful in the operation, but we have seen instruction sequences containing such useless instructions, like when we were trying to when we were trying to do that store into memory thing before. So this is the only useful instruction which we needed: move dword ptr esi edx. But we also had along with it pop ebx, pop esi, eda, ebp, ret. So we just need to save immediate values and make sure it doesn't and it's just useless. If there's a push edi here, it's not a pop. Pop would have been easy. You just put a value in the stack and then it would pop into edi and it's done. But push, it actually pushes and it will mess with the stack pointer. Okay, we'll see. I think they'll mention it somewhere. Which is okay. The first instruction adds the word at edx to eax, which is exactly what we want, right? The push instruction, however, creates some problems. First, the value pushed onto stack is immediately used by the RET instruction as the address for the next code sequence to execute, which means the values we push are restricted. Second, the push overwrites a word on the stack, so if we execute the gadget a second time, say in a loop, it will not behave the same. So this push is actually causing a problem. So should we go for a demo here to see why it's causing a problem? I think we can do that. cp exploit 3.py, exploit.py, exploit 3.py, 3.py, but this will still works on code 1, because we are not doing that heap thing anymore. We are just trying to understand this. So we don't need all this. We'll just remove everything. So we need to find a we need to find this gadget. Basically, we need to find this, and then later we can see building the exploit. So let's go back and we were supposed to just see how this push EDI adversely affects our return oriented program. So we'll just try getting that gadget. So we'll simply quickly use gdb to get it, -d. Okay, we'll assemble it first. We got it. gdb code 1 b main run. So we need to find 0xC3006A, right? Yeah, just copy it down here. 6A00C3. Perfect. Oops. Nope. None found. I mean, it happens. I think if this is a different version of libc, so it's possible. It's not a big issue. If this is not found, this is most definitely not found. You can see why, but we will vaguely give it a try. Okay, so this takes in only Intel syntax, right? So add ex comma d word of edx. Done. We'll delete all the other stuff. Okay. Oh, okay. So this is the different. This is weird, right? Look at this. C3 006A. Here C3 is 570203. It's actually pretty weird, but okay. Because it, like these 3 bytes uniquely signify push EDI RET. So, but when this, wait, I hope I've, yeah, see this. So, okay, this is actually very weird. Break it, main, will run, find, okay, we need to find in the reverse order, so we'll just push it away. 0x C3 7C 25, oops, I think I'm 57, sorry, 0357 0203. Okay, this is right. Oh, even that is not there. So, I mean, okay, so this is not there in a new version of libc. So what do we do for add? That's important, right? I mean, it's not there in the gadget. The sequence which they told is not present in our libc, but we somehow need to do that. So this is when we can go to libc's ROP, this generator, and then we can see. Okay, see, nice. We have something else. We have add dword ptr edx ecx ret. There's more than enough. I mean, there the register was first. It was the destination register, but that's okay. We can manage with that. So this is present. It's all good. So we can use this. This is not present, but something else is present, and we don't have this. We don't have to deal with this. So okay, because this is not there, we may not. We will chuck this exploit. But it was actually interesting to understand what problem this causes. We'll probably come back later. Yeah. Okay. We address these 2 problems as follows. First, before undertaking the add instruction sequence, we load into EDI the address of return instruction. This acts as a return oriented no-op. Okay, so you push something, but then it's a no-op. So it's a win-win. Counteracting the effect of push and continuing the program's execution. Perfect. Second, we fix up the last word in the gadget with the address of 1 as part of the gadget's code. Okay, that should work. Other arithmetic operations. So the sequence neg EAX RET allows us to compute minus x given x, and together with the method for addition given above also allows us to subtract values. So using addl and negative negation. Okay, so there is not in the sequences we found in libc a convenient way to compute multiplication, but the operation could be simulated using addition and the logical operations described below. Okay, this would be really costly, but that's okay. It doesn't matter if it's Turing complete. I mean, you just have to be able to do it. Doesn't matter how costly or cheap it is. So 5.2.3 XOR, exclusive OR. We could implement exclusive OR just as we implemented addition if we had available sequence like XOR EDX EAL or XOR EAX EDX, etc. Basically, these are memory locations. Note them, memory locations. But we do not. There are no such sequences. That's okay. Okay. We do, however, have access to a byte-wise operation of the form XOR B, byte-wise. Basically, in Intel parlance, it would be this XOR byte of EBX, AL. This is the XOR. This is the equivalent of XOR B %AL %EBX. Okay, so they found this, but they couldn't find these, the one which was equivalent to ADL. So okay, what do? If we can move each byte of EAX into AL, in turn, we can compute a word-wise XOR of EAX into a memory location X by repeating the operation 4 times, with EBX taking 1 values X, X plus 1, X plus 2, X plus 3. Okay, that is okay, byte by byte. Anyway, XOR actually means bitwise XOR. So here you're doing it instead of XORing 4 bytes together with 4 bytes, basically 32 bits, 32 bits. You're XORing 8 bits with 8 bits, next 8 with bits with next 8 bits, next 8 bits with next 8 bits. So like that you're doing, you're performing it 4 times. So that should be okay, not a problem. Conveniently, we can rotate EAX using the sequence ROR8 ROR8 EAX RET. Okay, so rotation is cheap that way. All that remains then is to deal with the side effects of the XOR B sequence we have. Okay, so they don't have a direct XOR B sequence. It has they have something like this. I mean, we will have to search for these two. We'll do that once we understand this. So they have, that's a byte of EBX plus so and so. Oops. Copy, paste, comma, AL. Okay, that's what they have. So they don't have a direct EBX cannot have the address. Instant, I mean, we know how to solve this. It's very simple. So EBX plus is equal to memory address, implies memory EBX memory address minus this. So we need to load EBX with that. So how can you load it? You can find a pop EBX RET, and we found a lot of pop EBX RET instruction sequences. I hope you remember that. So there are a lot of them. So this is solved. Let's see what. Okay, no, I'm sorry. They just didn't find this. It was along with some other instructions too. So this is the only needed instruction, but there were other unwanted instructions too, which cause a problem. Okay. The immediate offset in the XOR B means that the value we load into EBX must be adjusted appropriately. Yeah, that we can do. Okay. The AND OR operations, have the effect of destroying the value of AL. Correct. Look at it. The sequence they have is actually pretty tricky, because they will be storing the value in AL, the 8 bits of the EAX, and then later there is a stupid instruction which is doing an AND of 0xFF %AL. Okay, so this shouldn't matter because it's FF. It's you're bitwise ANDing with 1 1 1 1 1 1 1 1. So AL should be safe. This shouldn't matter. So okay, we'll come back. Okay, OR is also something like that. It's ORing with some value. So the AND OR operations have the effect of destroying the value in AL, but by then we have already used AL. So this is no problem. Oh damn, sorry. Okay, so AL is a source register here, destination is this. So yeah, we would have used AL. So even if AL gets corrupted, that's okay. We actually encountered something very similar with that ESI RSI thing. So see, look at this here. EDX is the source, ESI has the destination address. Once this is done, you pop some value in EBX. There's a pop ESI too. So this actually corrupts ESI register, but by then this is already over. So there's nothing to worry about. Great. Okay, I just got confused with the Intel and the X86 syntax. So sorry. Okay, so this is no problem. If we want to undertake any operation with the value in EAX, we must reload it from memory. Yeah, that is there. That's true. The push operation means that we must load into EBP the address of a RET instruction, and that if we want the XOR to be repeatable, we must rewrite the XOR operations into the gadget each time as described for repeatable addition above. So we saw what happens when you push something onto the stack. I mean, we kind of discussed, there was a push EDI in it. So here there's a push EBP. There's no difference. You need to load something else into EBP and then go ahead with basically you need to load the address of an RET and then make sure it doesn't mess up the stack. So yeah, we present a one-time XOR gadget in section A.2 in the web only appendix. Okay, great. And or not. So see, there are a lot of arithmetic operations. So it's only a matter of you spending some time and finding the gadgets. So we just did, so we found an add. So add also means you can subtract, and exclusive OR, we found exclusive OR. Like that we can also find and, or, not, etc. See, bitwise and or are also best implemented using byte-wise operations, much like the XOR method above. Okay, but you do byte-wise and then move the pointer. Great. The code sequences are respectively these and this. Okay, they found this in their libc 2.3.5 version, I think. So let us go to our sequence and see for ourselves what all we have in the store. Let's first search XOR EAX. Okay, there are a lot of XOR EAX, XOR ECX, XOR EAX. Okay, but they're not. Okay, so there's an XOR EAX, POP EBX, blah blah blah, RET. So XOR EAX, if you have the XOR operation working on the same operand, basically EAX, then it'll, what happens when you do when you XOR two same values? 1 XOR 1 is 0, 0 XOR 0 is 0. So EAX XOR EAX will clear off the register. It's actually really helpful. We'll talk about it later. So okay, so we have something XOR EAX dword PTR of EAX. Not really helpful, because EAX, it needs to be a memory location here, but then we need a immediate value, so this won't work. But there are a lot of things to search. I'm just trying to see what. Amazing. Okay, no. Here also it's EBX plus 0x5e. So we know how to get adjust the value of EBX, but because both operands have EBX, this is, I think, not so helpful. We'll continue. We'll see that. Okay, there's only one XOR EBX comma dword EBX. Strange. ECX comma. Okay, there are a lot of XOR ECXs. Okay, this is good. XOR ECX dword PTR EAX. Okay, but they need to end with RET. That's my problem. Okay. Nope. Okay, we'll find at least one of them. It has to be there. There's no hard and fast rule that it needs to be there, but if it's not there, then it's not Turing complete. PTR of ECX is done. Sorry, EDX comma. Awesome, crazy, we found it. So XOR EDX dword PTR EAX minus 0x7d. So we know how to work around these constants. So, and it's followed just by RET, so it's great. So we found it. So we have an XOR here, and we actually found a proper XOR working on a word than on a byte. So it's even more peaceful. But to make this work, we need a prerequisite like a prior instruction sequence, basically a POP EAX into which we need to load a memory location. So we will just search for pop EAX. Okay, there are a couple of them. Great, we have a normal pop EAX. Great. So XOR done, pop EAX, so that is done. We will search for OR EAX. Oh damn, this will list all the XORs too, so that's bad. Okay, so this, we have something here. Great. OR EAX dword PTR EDX, move word PTR EDX CS. So CS is a segment register. I don't know if we spoke about it, but it's a special type of register which is almost not used in day-to-day programs, but I mean they're special registers. We can talk about it later. But the point is, we found this. Okay, we'll actually make note of this, right? It's useful. We have a, we'll just copy this down in a very, okay, that is okay, but we have a lot of them. There's OR EBX dword PTR EAX 0xa and all that. So I think we will go ahead with this instead of this, because there is unnecessary unwanted instruction here, which I don't know, may cause problems later. We might have to arrange more gadgets to work our way around that unwanted thing. So we will leave it and we'll go ahead with something else. We actually found a gadget which okay, we found one for XOR 2. It was it XOR EDX? Shit. EDX. Okay, yes, it was this. So that's what they're talking about. So in I think in one of the sections they told that what matters is that this instruction sequence is present. It doesn't matter how many times it is present. We can keep using the same one again and again. So okay, we have, okay, we didn't find one for add, right? Or did we? We didn't. No, we need to find. We need all the instructions. We need all the type of sequences. Add. Add EAX. Okay, so we have nice. We have add EAX ECX, pop EBX RET. So EAX and ECX. So this can work, correct? ECX. We'll see if. Nice. This is crazy. How can we use this? Can you please think about it? This definitely needs a prerequisite. I mean, like a prior, gadget instruction sequence to prepare this. So you will need some pop EAX RET and then some pop ECX RET, right? So what do you need to add? So this. That's cool. We have a lot of. I think I'm pretty sure we will find a pop EAX, right? Okay. Just pop EAX RET. Great. Yeah. I mean, I think we actually. Shit. I'm repeating stuff all over again. We'll just make note and then move off. This will actually help us write the exploit easily later, that's why. Great. This is awesome. And we know how to store a word. Oops. We know how to store. Once everything is done, everything is done, we need to store, say, EAX back into memory. We can do that using the load store. So crazy. We have add, XOR, OR, all good. I guess the library just became more useful to write exploits. So okay, I'll just check if there are any questions. Okay, I think we have, I think MHSUN21 is watching the stream. Nice. Okay. So we were okay. We did AND. We found AND, XOR, or not. I mean, I want you to find gadgets, instruction sequences for and not. I'm mostly sure it'll be there. Or if it's not there, you need to find something like this, and you need to work your way around these, immediate additions, which we know how to do that. So I hope that is okay. Okay, shifts. Okay, these code sequences have a few side effects than 2 for XOR above, so they are simpler to deploy. Bitwise NOT can be implemented by XORing with the all one pattern. Oh yeah. So 1 XOR 0 would give you a 1. So if it's a 0, then XORing it with 1 would give a 1. If it's a 1 XOR 1 would give a 0. Nice. Okay, so this is peaceful. So you don't need a specific NOT instruction there. You can use XOR and simulate it. Great. So shifts and rotates. We first consider shifts and rotates by an immediate constant value. In this case, instead of implementing the full collection of shifts and rotates, we implement a single operation, a left rotate, which suffices for constructing the rest. Correct. If you rotate it enough, I think. Okay. A right rotate by k bits is a left rotate by 32 minus k bits. Perfect. So you just need a left rotate. A shift by k bits in either direction is a rotate by k bits followed by a mask of the bits to be cleared, which can itself be computed using the bitwise AND method discussed above. Perfect. So the code sequence we use for rotation is they have a code sequence ROL. I think it's the instruction ROL %C blah blah blah. We'll search for it. Hopefully we'll get that instruction or some. Okay, we actually got, but okay, we'll just search for this. Okay, this we'll first see if we can get. Oh, okay. This is not useful. Well, let's check this out. So it's ROL byte PTR EBX 0x61 or CL byte PTR ESI. So it has an R. That's okay. Okay, so it's rotating the. Wait, what is the? I don't know what is being rotated by what. Okay, 1 second. Rotating by a variable number of bits could use the same instruction sequence, setting ECX accordingly to the desired rotation amount. Okay, so the second operand is the number of bits you need to rotate. Great. So we found something useful. I think we found something useful. So here there is a role byte PTR ECX1 and it's a byte PTR. That's not useful. We need a D word PTR because we need to rotate 32 bits, but if we use a byte PTR it would turn out to be a bit complex. I think it would actually be, we'll have to do something, we'll have to implement something like this, the way exclusive OR is implemented using the byte-wise byte-wise instruction sequence which they got. But I think we can manage. The rest of it, add AH byte PTR EDX plus 0xa. So this means EDX need to be loaded with some valid instruction, a valid address, push CS. Now, if there's a push, then it's always a mess. But okay, ADC AL. ADC is the carry variant, adding the carry variant with, it's basically variant of add instruction, add AL, ADC, AL41, RET. Now we'll search for other role, but there are a lot of them. I think we can, if there's nothing else, we will be forced to use one of this, and we need to take care of all the the side effects of these unwanted instructions. I think by this time we are pretty ready to do that. We are well equipped to do that. That should not be a problem. Just search for it. Okay, great. So we've actually found a really good instruction here. Okay, it's a byte PTR again, but I think that's okay. ROL byte PTR, EBX minus some value which we know how to work our way around. 1. Pop DS. Popping something, if there's a pop DS, then it can be adjusted really simply. It's very easy. Okay, so we will make note of this. It's actually very easy if there's a pop. So rotate might actually come handy. I don't know. I don't think we'll be doing anything arithmetic in our return oriented programs, but okay, we'll search for D word PTR. Okay, this is awesome. This is exactly what we wanted. See, ROL D word PTR so and so 1 RET. So we can keep rotating by 1 that word by 1 any number of times. So with this we can simulate any rotation we want, and then there's a complete RET. This constant we know how to work our way around. So perfect. This is what we want. Okay, we are making some kind of, I don't know, vague progress. We'll remove this. Push this. So with that, I think we will go back to the paper. Okay. We can now consider shifts and rotates by a variable number of bits. The gadget in figure 34 reads the value of from the stack. If we wish for this value to depend on some other memory location, we can simply read. Okay, one second. Where's figure number 34? Wait, what? The gadget in figure 34. Do they actually mean figure 34 or something else? I think they mean this, because the gadget in figure, okay, reads the value of from the stack. If we wish for this value to depend on some other memory location, we can simply read that memory location and write it to the word on the stack from which ECX is read. I need to know what figure 34 is to understand this. Okay, not this. Oh, okay, no, there's actually a figure 34 which is part of, I think, the appendix. Figure 34. Okay, a gadget for rotating a memory word by a constant amount is given in figure 34. I think we have like a direct way. So let us kind of ignore that for now. We'll go back to reading different type of instructions, a different type of sequences in the X86 catalog. Where were we? We were here. Okay. So okay, it shows some gadget which we'll probably look into it later. Control flow. Okay. Unconditional jump. As we noted in sequence 4.1.4, an unconditional jump requires simply changing the value of ESP to point to a new gadget, as with pop ESP RET. So I think we already tried this. We tried to simulate an infinite loop here by popping the same stack value to the ESP. It keeps going back and again and again. So sorry. Okay, I think we know that. Figure 12 shows a gadget that causes an infinite loop by jumping back to itself. Great. We did that already. Figure 12. Okay, this. Exactly. So pop and then it points to the same instruction again, so you keep jumping back. Great. Conditional jumps. So, loops in return into libc exploits have been considered before. See Jera's esoteric number 2 challenge. Yes, okay. Conditional, I think we need to make note of all these nice I don't know, these small things which they tell, and then probably have actually look at them later, because once we are done with the paper, okay, I'll make sure I'll probably upload one more stream with all that. So okay, conditional jumps, these are substantially trickier. Below we develop a method for obtaining conditional jumps. Okay, so to understand conditional jumps, it will actually take a lot of time, so I'm skipping it now. We will skip this and we will go to system calls. We'll actually put it on our things to do list, because I myself, I've understood it, but I have not implemented any gadget like that, so it will take some time. Probably not today. I'll upload one more stream. We'll have one more stream with all these things. So conditional jumps. I'm sorry that I'm putting it onto the stack, but there's a lot more interesting things which we can do with system calls and function calls. So I just want to like move ahead and show you some cool stuff. So that's all, nothing else. So okay, skipping it. Okay, 5.4 to trap in. Okay, so we saw a couple of things. There were loads and stores, and there were arithmetic operations. We actually found a couple of really useful gadgets in the libc version I am using. So do try it on your laptop, on your system, on see what libc gadgets can you get. It may or may not be similar. See, I think we didn't search for what the gadgets they're using, but you can actually get better ones. So you can probably get gadgets with instruction sequences with only the necessary instruction, and not the useless ones which we have gotten, which are present in the middle, in between the useful and the RET instruction. So you can probably find that. System calls, right? To trap into the kernel, we could first load the desired arguments into the registers, and then to make use of int 0x80 RET or sysenter RET. Okay, so first, before moving to how a system call is executed, I'll just tell what a system call is. So we'll actually take this one more. So system call is like the instruction set that the OS offers to us. So how do you access the resources that are managed by the operating system? There are different resources. Say there is monitor, keyboard, mouse, there's memory, and then there is hard disk. There are files which you can write and read from. Say there are disk drives, there are USBs, microphones, etc. They're all resources managed by the OS. So how do you get access to that? So if you want to write something, into a file, you are basically accessing a piece of the hard disk and then writing into it, right? So how do you do that? So you can do that by the concept of system calls. So this fat thing is the operating system kernel. Okay, I realize this text font is really small. We will increase. Oops. Oh, 20. Yeah, 20 is fine. So okay, so this is great, but you can't access it directly. It gives a proper API to access it. That API is the system call API. So we can draw. Damn, I'm so bad at this. circle, and we draw a fat one. Okay, I want it to be transparent. Damn. Okay, fine, leave it. That's okay. That's fine. We can. Okay, so I'll just draw a lame line kind of a thing. Okay. Okay, you can think about it. This as the API. I want it to be a circle, but I couldn't make it, system call API system calls. So above this lie our applications. Our applications all are based on, they all use system calls. You want to write something into a file, you use the write system call. You need to read something from a file or from the terminal, from standard output, from standard input, you use a system call. You want to exit from a program, you use a system call. You want to spawn a new program, you use a system call. You use a system call for almost everything. Okay, so system calls are extremely powerful because they give you direct access to kernel's resources. So how can you execute system calls in a return oriented manner? So we know normally, okay, we will actually take a small, very small deroute. We will write a hello world program in assembly, so you will know what exactly what we are talking about. So data, so string, it's bytes, so hello world. So it's a new line. We are storing the string in the data section, and a new line and a null character. A string is it ends with a null character. See, in assembly you need to kind of mention that. So start is actually the first ever symbol that's executed by the program. For us as programmers, we always write the main first, but something should call main, right? I mean, main is a function, so a function should be called, and start is like the starting point of that of the program. The system recognizes start. So okay, that aside, move EAX comma, what is the write system call number? X86 32-bit. Really sorry, I've forgotten. This. Okay, not X86 64. I need it for. Okay, input output system calls in C. Great. Do we have numbers here? Nope. They're using the C wrappers for system calls, which are useless. Which are useful, not here, not useful here. Okay, I hope. Okay, so this is a 32-bit program. Damn, I think I need to Google. This is probably the most pissing off thing. Okay, this is the table we want. Okay, they don't have a 32-bit version. It tells coming soon. Okay, 4 is the system call number. So how does the kernel know what system call you want to execute? So they're all given unique numbers, right? So okay, so there's a sys restart sys call. So 0, you want to exit a program, it's 0x01. You want to fork a new program, it's 0x02. So write is 0x04. So 0x04. Note that we are writing a 32-bit program. That's very important because system call numbers are different in 32 and 64-bit. That's why when I open a couple of 64-bit, when I open a couple of websites which with 64-bit system call numbers, I didn't use them because they're different. So move EX, move that's a system call number. The first argument goes to so how does the system call look like? We can actually look at the man page. This will give the the C equivalent of it, so we can kind of do the same thing here at the assembly level. So I'm sorry about this. So the first argument is FD, so we need to write into standard output, which is 1. You might have come across this. 0 is the file descriptor for standard input, 1 is for standard output, and 2 is for standard error. So standard outs FD. Great. So and then constant void buff. Move ECX into str. Okay, there's some noise. Sorry. Buffer, basically hello world. Move edx comma the size. So it's 5 plus 5, 10, 11, 12, 13, 14 bytes. Okay. 14 and size. So now we have put in what system call we need to execute, we have put in the arguments, everything is ready. What you need to do, you just need to request the OS. How do you do that? You can do that using the int 0x80 system instruction. You interrupt the OS maintains, OS and hardware collectively maintains an interrupt vector table. Basically there are various types of interrupts. The 0x80th entry, basically I think the 128th. Okay, I'll stop till this noise. Okay, fine, let's continue, it's okay. So 128th entry in the interrupt table. So that entry will handle all the system calls, issuing of system calls. Basically you request and then we need to exit peacefully. So how do you exit? You call the exit system call. So we exit is 1, number 1. So 1. Move EBX, exit of some number, say 100, doesn't matter. So it's basically 100. You again request OS to kill the program. That's all you're doing. I use the NASM NetWare assembler code 3, right? NASM hello.asm. See, we need to generate 32-bit executable, so I'm using -f format elf. Just increase this. -f32. Now we have the object file. We'll link it ld hello.o object file with and give the output as hello. Okay, so I need to mention the architecture elf i386. Then you run. You got a hello. So this is the, I don't know for any of you who wrote this hello program. Actually, this is probably the first assembly program. Nice. It is this much. It takes extremely less amount of memory. So look at hello, it's just some 644 bytes. If we strip it, it might actually be less. See, it's actually 364 bytes. That's a hello program. I think if we make it a point to reduce the program size, we can actually probably reduce it to 200 bytes too, thinking about it. So anyway, the point was
that is how you call system calls in a normal program. So you load the system call number into EAX, you load the arguments into EBX, ECX, EDX. Okay, I want to make a note here. Where is the scratchpad? EAX equals system call number. This is for 32-bit. Let me specify that again. 32-bit. For 64-bit it's a bit different. We'll probably talk about it later in the next stream. I want to talk about ROP in the 64-bit scenario, because that's insane. That's amazing. So okay, anyway, arguments are passed in order, in this order: EBX, ECX, EDX, EDI, no, ESI. Okay, I think this EDI, ESI, I don't know. I'll just check. 32-bit convention, X86. Okay, I don't want the X86 calling convention. I want the calling convention for system calls. Okay, there is some. Okay, this is okay. We used EBX, ECX, EDX. That's nice. But what we need is, other. Oh, I think this order is fine as far as I remember. I think the next one is EBP. Yeah. So this is how. So if a system call has 6 arguments, you can pass here. I think more arguments you need to push them onto the stack. So that's how it is. So coming back to the program. Okay, this is the program here. So this is how system calls are called in normal programs. We need to simulate. We need a method to do the same in our return-oriented programs. How can you do that? Before moving forward, I want you to figure this out, because it's damn easy. It's really easy. So you need to load a constant into EAX. How can you do that? Okay, assuming you answered. So you can use the pop EBX, EAX instruction sequence if it's present, and pop EBX1, and here you need to load the address. The address is also one more kind of immediate. So even that. So these 4 are kind of, it's piece of cake in ROP. So we'll just try doing that. We will write a hello world ROP program. Okay, I think we'll do that. That will be cool. Hello exploit. Okay, CP hello. Sorry, we'll copy the old exploit. It has some useful stuff. Hello exploit py. Or we will actually, instead of exploit, this is a normal exploit, def exploit, we will write a hello exploit right here, and that's useful. And we'll keep calling hello exploit. That's it. So we need to copy certain things. That's okay. Okay, we may need the buffer address. Okay, that's we'll come to that. This is the gap. Okay, we actually need the buffer address. Let us store the buffer address. We need to store the buffer. We need to store the string somewhere. So how do we do that? Where do we store it? We'll come to that. So first we fill the gap, then writing hello, the string, somewhere. Where do you want to write it? So there are a lot of places you can write into. So one standard place is actually the data segment. So you might have, like, we kind of never spoke about data segment throughout ROP, but this is a very useful use case of data segment in ROP. So we can write it into ROP. We can write it into data segment, because we have seen the stack values keep changing, but the data segments addresses never change. You can see that under a condition we'll see that. So writing the string to to data segment. For that we need to know the first address of data segment, database address. How do we find? Very simple. So we'll use GDB, we'll run it, look at the maps file, and then with maps file we have everything, right? Okay, do you have any questions? Anyone? Okay, no, they are all my friends, users. Okay, so we can let's go to this. Okay, and then the data segment, the read write segment starts at 56557000. This is the database. Great. So we will use that. Oops, wait a second. I think my RAM is 4 GB, so if I have too many tabs open, I think that will cause a problem. Okay, just close off everything. If you need, we'll open it. Okay, just close this up. Okay. This is the base address. Great. So we need to write stuff here. Writing is nothing but storing. So I hope you remember the storing a word into a memory, which we did. So we'll use the exact same thing and then write it. Okay. So see here we wrote something into memory here. Memory address is this. But now we need to write the string. A string is nothing but an array of bytes, nothing else. So let us start writing. So we need to write. You can see that these are d word. It's a move d word esi comma edx. So you need to move 4 bytes by 4 bytes. You can't write the whole string, say 13 bytes into the memory directly. You need to write 4 bytes by 4 bytes. So we'll do that. We can slowly, peacefully do that. Okay, payload dot. Okay, we'll actually copy all this stuff. Okay, this can actually be a pretty long exploit, I would say, because there are a lot of things which we need to write, right? Storing a value. Okay, so this is the first. Storing a value. We know the memory address. First, the 4 bytes is HELL, right? So memory address is this. Value is, okay, we'll just data. Okay, value is the ASCII of HELL. So we can get that using ASCII -x. HELL. H is 48. 0x48. Small e is 65. Small l is 66. See, 60. So first we need to write this. Let's write it. Memory address and then value. Okay, so that's all we had to do. So if you remember, these things we didn't have to change a thing here. All we were in full control of the memory location, memory address, and the value. Give me a moment. I'm sorry. So I think so we are at so we didn't have to change anything here. All we had to do is we just change the memory address and the value, and we are done. So we have payload to write the first 4 bytes. Now next 4 bytes slowly we'll write it, no hurries. So here memory address is not this, it's 4 bytes, data plus 4, because we have the first 4 bytes, the data is already present. It's hello world. Wait, where's the string? O space WO. Okay. Okay, we could have written a loop. Shit. Okay. Never mind. O space WO. 6F 0x 6F O 0x 20 space is 20. O space W, where's W? 57, and then again hello world 6F. Great, and that's it. Let's just copy and paste. I hope you are able to understand what is happening. So it's 08 now, and we are writing 4 bytes by 4 bytes. I mean, there's no other. Hello WO RLD exclamation, RLD exclamation. So R is 72, 0x72, R small l is 6C, correct. D is 64, correct. 64, and where is the exclamation? Exclamation is 21. Okay, so we have. Okay, we need to write the null byte. I mean the space and the null and the new line. I'm sorry, null and the new line. C plus 12. So here we write 0 0 0 0 0 0 0 0 0A 0 0 or no, 0 0 0A. So with that we have just written the string, that's it, nothing more. We still need to load. So now system call comes in. So load 4. So basically EAX is equal to 4. How do we do that? So we actually had found a pop EAX. So we will quickly use RASM to find the the value using RASM and GDB. I mean the same technique we have been using so far. So find, so it's 0x 6358. Sorry, 0x C358. Okay, there are a couple of them. Awesome. So we'll use the first one. I mean, no problem. X/2i, just need to verify. Yes, works. So here payload, one sec. Payload, where does this it needs to return to? So before, when we were doing the store thing, storing the value into memory, we didn't return to any specific address, we just return and it crashed. But we now need to return to a sequence which will load the number 4 into EAX. So struct.pack this address, pop EAX RET. So what do you need to pop? 4. That's enough. Just writes syscall number. Okay, that's done. So now we need to load EBX is equal to 1. 1 is basically the standard outputs. This one standard outputs file descriptor. Okay, so RASM2. We'll search for, okay, yeah, I mean, we obviously know there are a lot of POP EBXs. POP EBX RET. Okay, find 0xC3 5B. There are a lot of them. Okay, we'll just go ahead and use the first one. It's in code. It's in code one, the program itself, but that shouldn't actually matter. POP EBX RET and what do you need to pop? 1. Simple. std out fd. Standard fd, standard file descriptor. So later we need to load ECX is equal to buffer address. So what is the buffer address? We have stored the hello world string in the data segment. So we have an address already, right? Nothing to worry about. Okay, but we need to find a pop ECX. If we don't, I mean, we'll have to use something else. So we will see. We will get the address first. 59C3. Okay, we'll come out of this. Find 0xC359. Okay, awesome. There are a couple of them. Okay, there are POP ECX RET. So VDSO. Okay, some VDSO is one more address range. So it has that. So we'll go ahead and use it. Okay. POP ECX RET. What do you need to pop into ECX? You need to pop the data address. Okay, I wish we had a database address. We have a very good nice database address. See, we are writing a really, I mean, we could have written this exploit efficiently. I mean, a loop here and stuff, but we'll just, that's okay. We'll make it efficient later. We'll just write like a working exploit now, just to understand. So buffers address. So that is done. And then now EDX is equal to string length, which is 13. We know that it's 13. So even here we need something like that. So we'll see if we find a pop EDX. So it's 5AC3. I think by the end of this stream I'll be like, I would have memorized a couple of opcodes of a bunch of instructions. I think 5A. C3 5A. Nice. So we have a pop EDX. So that is great. We have pops for all the registers which we need. That's amazing. Back. Pop EDX RET. What do you need to pop? You need to pop the value 13. Okay, we already have that. So it's string length. Now we need a way to execute the system call, which is int 0x80 or sys enter. So request. Okay, we have to first search it. So the RASM int 0x80 RET. So CD80C3. We'll see if we can find that. It's hard without doing that, but 0xC3 80CD. You know why we are putting it in reverse order, right? In the memory, it's all in the reverse order. It's in little endian format. So great. So the dynamic linker has it. x/2y this. So the dynamic linker has it. I mean, if it's present in the address space, we have all the liberty to use it. So no one can stop us. Pack little endian in 0x80 RET. Great. Now we have something like a proper ROP exploit, I would say, where we are printing hello world, not taking control of the system, but that's okay, some step. So we'll execute, we'll see if there is any problem with the Python script we have written. Okay, there is. Return stack address. Shit, I didn't. Line number. Return stack address not defined. Line number 46. Ah, okay, great. Okay, I just need to copy these. Yeah. Okay, so with that we are good to go, I guess. So look at the payload now. Wait. Oh, okay, we had to write the payload. Should we actually miss these 3 lines? Okay, writing the payload is obviously at most important. Okay. The payload is huge. So I think the actual ROP program, the program which we see here, it's actually way bigger than the junk which we put. So okay, we are progressing in life, I think. So we have an exploit, so we will actually use GDB and see if we can run it. Cat, oh no, GDB code 1 will break at func run payload. Okay, we'll go through each and every instruction sequence. I want to make sure you understand this. So first is the pop ESI. We'll have the exploit here. Oops. See, the hello exploit starts here. So the first address is this, the pop ESI, this one. So we enter that. Pop ESI, pop EDI, pop EBP, RET. Okay. So now we are popping. What are we popping into ESI? We are popping this, which is the data section's first address. ESI has that now. Look at it. Where is ESI? ESI has it. C56557000. Now these are crap, and then we return to pop edx ret, where we actually write the value, that the first 4 bytes, the HELL. Okay. Oops. This is fine. Okay, and then so we actually wrote, so we didn't see the writing part. So this move dword ptr esi edx is the writing part, so we can actually check w 0x. Oh, it's stored in the, okay, so we had to store it in the reverse format because it's little Indian. Damn. Okay, that's fine. We'll get some weird hello, like the ulta hello world, but that's okay. So it's stored here. You can see that ESI is pointing to HELL here. That's okay. The order is different, but that's okay. And we can continue. So these, okay, so this has 4 unwanted instructions, but we only put 3 junk values on the stack. Okay, so this won't work, because now pop EBP, it will actually pop up the like the instruction address of the instruction sequence, which is not needed. So exploit is doesn't work. I think we messed up here. There's a pop EBX, which we didn't see here. I don't know how I missed it, but that's okay. I mean, all we need to do is okay. All we need to do is have one more of this crap. I mean, the 4 bytes of crap. So we'll just copy it everywhere. It shouldn't matter. Print P, and then okay, the 4th. Okay, so okay, there's one more. We'll just correct it off. So we had to store it in the reverse order because it's little Indian. Should I keep getting confused with this? 0x 6c 6c 6548. So this is in the reverse order. So while storing it, will store properly. That's the thought. Same here. 0x 6f 57206f. Okay, 2 more to go. Oh, I'll be so excited if this Hello World program works. 0x 21646c72. Okay. Okay, so this is 0x. We want it in 00000A00. So while storing it, it will store it as, okay, we need it. No, it was actually in the right way. Sure. Okay, we need it this way. So while storing it, will store as 0A and then null byte, and rest of them are anyway nulls. So run the exploit. Okay, we'll go back. We will run the exploit again. Okay, now we start. I think now we are like set. Okay, RET pop EDX, write hello world, hello. Okay, and then now it's trying to write it. It actually wrote it. See, ESI is pointing to the data segment and the first 4 bytes are HELL. So writing it is done. So these 4 are unwanted, so we'll simply get it over with. Then now you're popping the next address, the 4th data plus 4 address into ESI. So you keep doing this. Pop OWO into EDX. So EDX as hello world. So it has that, and then return, and then you write it. So now the data segment, the starting of the data segment should have like the 8 bytes. So we will look at that if it's in the string form. So look at that. I hope you are able to understand this, because this is the starting of the data segment. We stored the first 4 bytes and then later the next 4 bytes, the O gap, the space, and then WO. So that's something. Okay, so let's move. This is unwanted. Now again ESI, that's a data plus 8, the A2. Okay, and then you write it again. Writing is done. We can check. Hello world is there. We just have the new line and the space to finish it with. Okay. Okay, I think we messed up. It entered something which was unwanted, which was not intended. So here pop EDX, it popped, and then it had to return. It should have returned to, okay, this is not the value. This is not the value which we put. I think we messed up the exploit. Okay, let's go back to the exploit. That's it. So the writing was all done properly, that was working fine. At the end of this pop edx, okay, so this had to be written, and then this, okay, but something unexpected happened, which is what we need to see what happened. Okay, we'll quickly move forward. The first 3 iterations were fine according to me. Okay. So what all do we have in the memory now? Okay, we have hello world. We'll have a close look at it now. EDI, BBBB, BBBB. Now we'll return to EDX. Okay, pop EDX. Okay, so here there is a null byte. That shouldn't matter. Okay, so I think because it is seeing a 0 0, it's okay. I think that's the getS's problem. So what getS does is it will stop taking input if it sees a new line 0A. So as soon as it saw new line, it stopped. So it just took input of these. I think that is the problem. So that's okay. We'll end it with a null. We won't have a new line, but that shouldn't cause a problem. So we are popping 0 into EDX. Okay, and then where are we returning to? We are returning to some unknown value which is not intended. We need to return to this, right? 0xfd 0xf7df818c. We need to return to this value, but we are not. Okay, I get the problem. The getS just stopped taking input. It stopped taking input as soon as it saw a new line. So all this is just not there on the stack. I think you're able to see that. Nothing is there. It's all crap. Our exploit. So it saw a new line and it just stopped taking input. So we will just remove the new line. We want hello world. That's enough. We don't want this. We don't want this. Hello world is enough for us. Or hello world ending with a null. Okay, this should be fine. So okay, I'll explain the problem again. So getS stops taking input when it encounters a new line. So because we put a new line here, it stopped taking the input and the rest of the exploit was not copied onto the stack. So none of this is there on the stack. So that is the problem. So okay, good. We got the problem. Happy about it. So we have the payload. We just need to run it again. And go ahead with the input. Okay, just I think we can just run through because we caught the problem properly. Okay, pop ESI. What does ESI have? Okay, fine. Pop EDX null. Okay, great. Now we are writing it. So this was the fourth write, the fourth 4 bytes write. So we can now actually look at the memory and see what's there. It's hello world followed by a null. We aren't able to see the null, but I think the null was there already. So okay, now here is the interesting one. So now data is written. All we need to do is execute the system call. So pop EAX RET. So 0x4 is the right system call number. We will pop return to pop EBX. See, EAX has 4. Great. EBX is basically 1, which is the file descriptor of standard output. And then ECX is the address of hello world. Okay. You can look at it. EAX has 4, EBX has 1, and ECX has the address. And where are we? EDX, the third argument, has the number of bytes. So let's go for it. Now is the we have the system call number and the arguments. We just need to, did it execute or not? It executed. This is the hello world program. It actually printed hello world. So now it will return and it will probably crash. Yeah, it crashed. So this is what I'm talking about. So if you want more of, like a exploit fields, you can try it out without GDB. I use GDB because I wanted to go through stepwise, instruction sequence wise, so that you get a clear understanding. But we'll just do this. See, it printed hello world. It printed hello world, and then it will crash. That's okay. So that was the hello world exploit. So what we can actually do is we can actually end the program peacefully, right? We can call the exit system call and then end the program peacefully. So call exit. Calling exit is very simple. Just pop 1 into EAX, pop some other value into EBX, and then call. We all have that ready here. We'll just copy it. See, we have it right here. This is all we wanted. EX is 1 though. Exit system call is 1. So it's exits system call number. Oh, you can do exit of 1. That's cool. And then request the system. Oops, sorry. Request the system call. That's it. So here we are. Till here we know what happened. Printf hello world printed properly. There was no doubt about it. But we want the program to exit properly. I mean, this is just you can just play around with it any way you want. Now that you know, you can execute any system call and then just play around with it. It's totally up to your imagination that what you can do. So that's it. It didn't crash. So exit system call executed properly. Whew. So that was some actual return oriented code, I would say. So we used a lot of concepts here. We wrote into some data segment which we had not thought about before, and then we used the load stuff into the memory, the store a value into the memory sequence which we had written before, and then we used it again and again repeatedly to write the complete string into the data segment, and then we called a system call. So if you're able to call a system call, then that's probably you can do whatever you want. You can see that you can do whatever you want. You can change every system is really powerful. So every system call is really powerful. So with system calls you can actually do whatever you want. So okay, coming back to system calls, let's continue. So I hope you got an idea of how this worked. Okay, on Linux we can instead look for an lcall %gs0x10 instruction. This will invoke the kernel vsyscall in linux gate.so.1, which will in turn issue the sysenter or in 0x80 instruction. Okay, but okay, yeah, that's probably true, but that's not necessary. because we got this N0x80 RET. We already have it. It's there in libc, so that's peaceful. We detail in figure 15 a gadget that invokes a system call, arguments to be loaded ahead of time into the particular registers in order: EBX, ECX, EDX, ESI, EDI. Okay, so that was the mistake. Okay, so this ESI and EDI. Okay, I'm sorry for that. We have left space in case the vsyscall function spills values onto stack, as the syscenter based version does. We are anyway not using the syscenter version, so we don't have to worry about it. Note that the word pointing to lcall would be overwritten also. A repeatable version of this gadget would need to restore it each time. Okay. So that was about system calls. We actually translated the normal hello world program into our return oriented version of the hello world program. So that was, I felt it was cool. So function calls. Finally, we note that nothing prevents us from making calls to arbitrary functions in libc. We have already seen that in the first stream. So we can call any function with any number of arguments using this. So this is in fact the basis for previous return to libc exploits, and the required techniques are described in by Nergal 2001. Wow, that's great. The discussion of frame faking is of particular interest. So if you remember, we actually constructed a fake stack frame and then we executed system. So we can actually look into that again if you would like. 6 faking frames. Okay, we have a lot of things to visit. A special stack frame should be reserved for the called function as discussed in section 6.x. Okay, so now we have come to the last section of x86 catalog. That's the shell code. We now present a return oriented shell code. Our shell code invokes the execve system call to run a shell. This requires, now I want you to write, let us not look at this. This is okay, but let us not look at this. We will write the complete exploit on our own. So without using that. So we will call this def execve exploit. Okay. All we need to do is get a shell. The complete. Okay, one second. I'll just see if there are any questions. No questions. Great. Just increase. So all we need to do is get a shell. How do we get a shell? Thinking from a function point of view, like the executing functions, we can use system or execve. But here we are thinking from a system call point of view. We need to use a system call and get a shell. Getting a shell is nothing but running a new program. What is that program? That program is bin.sh. Where's the scratch pad? Great. So we are probably at the last part of today's stream. After this, I think I'll end. It's been too long. So execve exploit. Great. So here, calling execve, you know how to make a system call now. So you load the system call number into EAX and pass the arguments, and we also have all the gadgets, all the instruction sequences needed to execute a system call. So that's not at all a problem. How do you call the execve though? That's I think what we need to look into. So for that we will look at the execve's syntax. Man execve. So execve takes 3 arguments. It returns an integer, doesn't matter. Const char file name, the file name basically. EAX should be the system call number, which is okay, we actually deleted everything. Okay, this gave the Linux kernelgrok.com. That's good. Search execvg. We want execvg. So that's 0x0b. That's 11. That's 11. So ex should be equal to 11. The first argument ebx is equal to first arg should be equal to const char file name. Basically, it needs to point sh. Okay, so that was done. Ecx is equal to const char argv. So this is the argument vector. So this should be a pointer to a pointer. So pointer. Okay, so we need to have something like this. Argv. We can actually put a null here. I mean, I've tried it before. Actually passing argv it will be amazing, but we can pass a null and we can actually get away with it. So edx can be null. We don't care about the environment variables. We can pass null to it and then int 0x80. This is a very minimal shell code. So it'll just work and that's it. Okay, so ebx first argument is address of ebx. Okay, before that we need to copy some prerequisites. We can make this efficient. We'll do that later. So now we need to get the address of bin sh, right? So there are two options here. One option is either we write bin sh in data segment and then get the address, which is very peaceful, which is easily doable, or we can see if we can find bin sh somewhere in the memory. And last stream we actually saw that the libc, or I think the dynamic linker, already had the bin sh string. So we'll actually get the address. So find string /bin /sh. So it's actually there in libc. That's really peaceful. So let us start with, okay, no, that is, we'll just make a note here. We'll make a note here, but we need to start with, we can do it in any order, but let's start with system call number payload equals struct.pack. We can actually copy stuff here. Okay, we can actually copy everything from here, literally everything. So we'll just copy the complete thing and then just edit it. Okay, that's great. So I hope you're able to see this. Ex is 11. System call is execvg. It's no more a simple write. This is a very powerful. So pop ex, and this needs to be 11. Great. Pop ebx. Now ebx is null. Oh, sorry, ebx is the argument, so it needs to be this address of /bin /sh. Okay, so this, well, we don't need this comment. ec should be null, so let's simply put 0. Okay, and this also 0. Okay, so just ecx is argv, which is set to null here. I hope it doesn't ruin our exploit. So 0, and then we call the system call. That's it. It's actually very simple that way. We will go ahead and call not hello exploit, but we will call exec VE exploit. That's it. So we will call it .py. So this is some payload. We will go back, break at func, run the payload, run the program with payload. Okay, getS is done. Now we will go through instruction by instruction, see if actually execute or what happens. Okay, wait, why is there a pop EDX here? I mean, there's something wrong. Okay, we had to call, one second, where is, so we had to call exec VE exploit. I think we did that. Correct, but there was HCLL, I mean okay, we'll run it again. I don't know what happened, but it was wrong though. Okay, it still has the HCLL hello world program, but I don't know why. Hello world is okay, but we need to get exec VE working. Okay, so I again forgot to copy the writing part. So basically it's not writing to the payload.txt. Okay, now we have the payload. We'll go back, break at func, run with payload. Perfect, we are ready. So first we load 11B into EAX. We are seeing that. So EAX should have 11. Okay, EBX should have the address of /bin/sh. That's cool. It has, and then ECX has a null. EDX also has a null. Now it's the testing time. So okay, so process 2711 is executing a new program /bin/dash. So we got a shell. So debugging mode is over. Let's go back to real mode. So we got a shell. Okay, it would have been really cool if I'd got a root here, but that's okay. I mean, we got a shell, so you can do anything here. Yeah, you can't clear because okay, the environment variables are not there, and this clear depends on some term environment variable. That's okay, but you can do a lot of other stuff. You can literally do anything. So we wrote an exploit which will fetch you a shell. That was actually fairly simple in front of the hello world program, I would say. Hello world return oriented program. So let me go through it again. Let me revise what is that? Exploit.py. So writing an exploit, when we have access to the system calls, when we can execute system calls, we can do really powerful things. It is too powerful, so we'll just go through it. So we covered the gap here. First we filled in the system call number with using this pop EAX RET sequence we found, and then we filled in the first argument, which is the address of /bin/sh into EBX, which is the second argument, and then the other two are null. So, and then we requested the OS to please get us a shell, please spawn a new program. So with that we have completed. So we'll just, for the sake of it, we'll just run it once again. So we have a shell here. using ROP. It's totally pure ROP. We didn't use any function. It's only a bunch of instruction sequences chained together in a meaningful manner to give a shell. So let's go back to the paper now. Enough of so setting the system call index in EAX to 0xb, setting the path of the program to run EBX, the string this, and then you know what else. So I want you to read this section. It's actually pretty simple. It's very easy. So suppose that the libc is loaded at the base address so and so into some program. Suppose moreover that this program has a function exploitable by a buffer overflow, like the one we took, with return address stored at some stack address. This is the stack address. In this case, the shell code given above yields. So let us look at our shell code, our return oriented shell code. It's probably more inefficient than the one given in the paper, but it works just fine. So this is where the shell code starts. This is the shell code. See, phi e b b d e f7 0b 000000 d9 53 55 56. So this is the shell code. It works. In this case, the shell code given above yields. So how many bytes are these? So 4 and 4. So it's 16 into 4, 64 bytes. Our shell code is about 16 plus 16, 32. Okay, 36 bytes. That's good, but there should be some problem. Anyway, note that there is no null byte except the very last. Okay, this is where our exploit will actually might fail. So it depends on the function you use. So in code1.c, I purposefully used getS because getS won't stop taking input if it encounters a null. It will stop taking input if it encounters a new line. So we have there are a lot of null characters in the middle. So you can look at it, null. But getS didn't stop. It just took everything. But if we had used some other function like strcpy, string copy, or memcpy, or something like that, any other function, it would stop copying or stop taking input if it encounters a null. So if we had used string copy, for example, to copy this payload into some other buffer, so it would take in 5e, bb, de, fb, f7, 0d, then it would see a 0, 0 and it will stop. The rest of the exploit is not copied and the exploit would fail. So their exploit code, the shell code, is higher only because of that. They have made sure there are no null bytes in the exploit. So I mean, it's the cost you pay if you need a no null byte shell code. It's actually more robust. It will actually work better. So we can probably look into how to write no null byte shell code. That's an interesting exercise. It's very hard to remove null bytes from the shell code, because somewhere or the other you might be using null bytes. So anyway, so that was the shell code. I mean, we wrote some basic first we wrote ROP program to execute hello world, to print hello world, and then we wrote a program to execute a system call, and then which executes execve, which in turn executes a new program itself, right? So that is how powerful ROP is. So like all other examples of return oriented shell code, oriented code presented in this paper, this shell code uses only code that is already present in libc and will function even in the presence of W XOR X. Same. We have used, we are obviously following the paper, we have used code sequences only present in the address space, which are probably present in libc and probably one or two present in our program, like that pop ebx ret. So except for that, it will work just fine, and it will work even in the presence of W XOR X. Yes, because we didn't inject any code and we didn't try to execute it. All we injected were addresses which pointed to instruction sequences somewhere in the memory, say libc or code2 or somewhere, and immediate values associating with it. So there we stop today's stream. Section 6 talks about Spark Gadget Catalog. I will definitely, I don't know anything about the Spark architecture. I want to learn. I will learn and probably get back probably in a future stream. So that will take some time though. But that was about ROP. Section 5 would actually conclude ROP. So actually there is a lot more. There's section 7 which actually deals with a gadget framework which they came up with, and then they have a, okay, so this is a example Spark exploit. Okay, they have an automatic more complex framework exploit. They have made a compiler, return oriented compiler, which will take up all the gadgets present and then it will generate code. So what we did, we manually wrote each and every line, each and every memory address, each and every immediate value, but here the compiler will do it for you. That's the idea. So it's completely automated. You can see how it will get harder if you want to write harder and harder, longer exploits. So a compiler would, sorry, where were we? We were, so a compiler would actually help in writing better exploits. I mean, obviously we can definitely write exploits, but it will take a lot of time. So conclusion, I don't want to read the conclusion because in the next stream I think I'll probably be reading the conclusion. That's because, going back to the scratchpad, we have certain things to visit. These are all things to explore which are really interesting, which will only make our exploits nice and robust. Say things like two-stage exploits or even mitigations. We didn't see what type of mitigation measures have been administered in the operating systems to mitigate attacks like ROP, because WXRX is totally defeated here. So yes, there are other really effective good mitigation techniques. We will look into that. They've also written a selection sort program using just the gadgets present in the C library. That's amazingly cool. That's really cool. They've used the compiler. I mean, that's why they were probably able to do that. With that, yeah, they also presented algorithms which can help us to write that tool. Basically, parsing through libc and finding all the instruction sequences. Say stop at a return the C3. Okay, stop at C3 and then you move backward and all that. Basically, those algorithms. So that we can probably see in the next stream. I thought we could finish the whole paper in 2 streams, but no, bad luck. I mean, I hope I went into good depth and you were able to understand it. Let's see if anyone has questions. If not, we'll sort of end the stream. Okay, nothing. So with that, I will just summarize. I'll take 2 more minutes. I'll summarize what we have done so far, and then we will end the thing. So we will just go to the scratchpad. We have everything ready, right? I mean, whatever we have done today. So we'll just read through the scratchpad once, and that should be fine. Okay, we started here. We started with the foundation of ROP with the question of how will the program look like if stack pointer points to the next instruction to be executed. Starting with that, we need to see NOP Sled. Okay, we'll do that. Starting with, we kind of took a couple of examples. We saw live demos of POP, Reg, RET, and etc. We built a simple, infinite loop using POP, ESP, RET. That was kind of cool. We left the conditional jumps. That will take time. I mean, even I have to explore it properly. We'll probably do it together in the next stream. So store, and then I think the main thing we did was store a random value into memory. We did it all by ourselves. So we took we identified this. This was the type of gadget we needed, and it needed two other primitive gadgets like pop reg 1 and pop reg 2. So we found all that, and then that was done, and then slowly we started looking at the gadget catalog. There are different types of gadgets: load, store, arithmetic and logical operations. And then when we hit system calls, that's when we wrote the assembly program, like the normal ordinary program, and linked it, executed it, and then we also wrote the return oriented programming equivalent, ROP equivalent. So I hope you understood that clearly. And then to end it, we wrote an ROP program to call a new shell, which is probably the end goal of any attacker, using the exec.ve system call. So that is what we did in today's stream. I hope you liked it. I really enjoyed teaching it. I mean, I was thinking of stopping at, I don't know, 3-4 o'clock, but it went till 6. But I mean, I am sort of satisfied with the content like the amount which I've covered. I couldn't complete the paper. I'm a bit sad about that, but I didn't want to rush and sort of hurry things up, because this is a very interesting paper and it was quite tricky for me to understand in the first place. So if this is your first time reading this paper, I don't want you to have any sort of doubt when you're reading this paper. So I hope I've done justice. Anyway, we will, in the next stream, we have quite some work to do. There'll be more of writing exploits, spending time on understanding these, say ROP and heap or NOP Sled mitigations, two-stage stack-heap exploit. This sounds amazing. Conditional jumps, faking frames. So this doesn't involve understanding anything, so you know what ROP is. I want you to write these exploits on your own. Try to get, so just don't execute some bin as such. Try to execute any other program. So we also anyway, the programs would sometimes need arguments. Here arguments, we set it as null, so that's probably one more thing we can visit. Setting up argv. It's not a big thing. I mean, it's not really hard, but yeah, we'll do that. So I want you to, I mean, if you have time, you can go through this again, go through the video, and at least try to write the hello world and the exec.ve ROP exploit again. I think that will clear up a lot of doubts if you have any. So things to visit. So these are the 7 things which we need to visit. So I think with that we will end the stream. We'll close up everything. We'll end it. Bye guys.